the next point is when the number of zeros in the transfer function is greater than or equal to number of poles in the transfer function, then it is said to be the high pass filter. When the number of zeros in the transfer function is greater than or equal to number of poles in the transfer function, then it is said to be high pass filter. Why it is like this? So listen carefully. Suppose there is a transfer function like this. The transfer function is the ratio of the numerator by denominator. So here, suppose there are more terms. Here there are more terms. Here there are less terms. So more terms means we can say zeros are going to give orbit of each term is going to contribute close to the decimals per decade. Whereas here it is having basic less terms. So each pole is going to contribute minus 2 decimals per decade. So if zeros are more means we are going to get more and more plus 2 decimals per decade means the graph will go like this plus 2 decimals per decade more and more. So we can say finally we are going to get like this. So we can say this is said to be basically we can say high pass filter. So we can say high pass filter because we are having more and more plus 2 decimals per decade. So finally we are going to high pass filter. Suppose if you have more and more poles means we can say we are going to get more minus 2 decimals per decade. So we are going to get minus 2 decimals per decade. And finally we will get like this. So we will get like this one. So this is means definitely we can say this is like low pass filter. So this is the low pass filter. Therefore we can say more number of zeros, the given transfer function with more number of zeros means we are going to get more plus 1 decimals per decade. So this is basically high pass filter. Suppose if we have more number of poles in the transfer function, so we are having more number of minus 3 decimals per decade, so we are going to get the low pass filter. So this point always you have to keep in your mind. So finally I can say in a given transfer function, if you are having more and more zeros, then we are having more close to the decimals per decade. So therefore we are going to get the high pass filter. Suppose in a given transfer function, if we have more and more poles, means we are getting more and more minus 2 decimals per decade. So therefore we are going to have the low pass filter. So finally the next point is the Laplace transform of e to the power of minus t into u of t, which is equal to 1 by s plus 1 whole square. It's a very simple thing. I have already told you the Laplace transform of t is nothing but to the power of n factorial, it is n factorial by s to the power of n plus 1. So here t is equal to 1 here. So substitute is equal to 1. We are going to get 1 by s square. But again, Laplace transform of e to the power of jt, e to the power of minus at into f of t is nothing but f of s plus a, here a is equal to 1 here. Substitute in place of s plus 1. So we are going to get 1 by s plus 1 whole square. So that you always have to remember two important formulas, which is the Laplace transform of e to the power of n is n factorial by s to the power of n plus 1, and the Laplace transform of e to the power of minus at into f of t is equal to f of s plus a. So these two formulas always you have to keep in your mind if you want to solve this type of questions in a very fraction of seconds. So these things always you have to keep in your mind. So finally I can say the formula which is the Laplace transform of t to the power of n is nothing but simply we can say that n factorial by s to the power of n plus 1 is the Laplace transform of e to the power of minus at into f of which is f of s plus a. The Laplace transform of t to the power of n is n factorial by s to the power of n plus 1. And the Laplace transform of e to the power of minus at into f of t is equal to f of s plus a. So these formulas always you have to keep in your mind. The next point is gain margin. Gain margin means the ratio of the critical value of gain for a system by the operating value of the gain for a system. So critical value means a gain more than this one means definitely the system will be unstable, and the operating value of the gain for a system. So this ratio is called the gain margin. So if you want the gain margin in dB, then 20 log of gain margin with a base 10 in a dB. So I have already told you what is the actual formula of gain margin. Gain margin is equal to 1 by mod of g of s h of s at omega vc. So this one I have already told you. This is the actual formula. Either you can solve with this method and this method, and maybe you are going to get the same result. So here the gain margin is the critical value of the gain for a system by the operating value of the gain for a system. So you can write like this, which is simply we can say k critical by k operating. So this one always you have to keep in your mind. So k critical by k operating. This point always you have to keep in your mind. So it is a ratio of the k critical by k operating. So this one always you have to keep in your mind. In the gain margin in dB is nothing but 20 log of gain margin with a base 10 in dB. So these things always you have to keep in your mind. So finally, I can say gain margin is nothing but is the ratio of the critical value of the gain for a system by the operating value of the gain for a system. So gain margin in dB is nothing but 20 log of gain margin with a base 10 in dB value. So I've already told the actual formula, which is gain margin is equal to 1 by part of G of H of S and omega PC. This goes of frequency. All this is I've already told you. So either you can solve in any of these methods, still you are going to get the same result. So finally I can say the gain margin is the ratio of the critical value of the gain per system by the operating value of the gain per system, which is K critical by K operating. Shortcut remember, C is going to come earlier than O. So after C you are going to get O. Gain margin dB is another 20 log of gain margin to base 10 in dB. So or you can go for the other method also. Gain margin is 1 by mod of G of H of S at omega PC. In any other method you are going to get the same result. The next point is 20 log 2 to the base 10 is equal to 6 dB. So this one always you have to keep in your mind. So therefore we can say 20 log 2 to the base 10 is always equal to 6 dB. 20 log root 2 to the base 10. Root 2 means 1 by 2 is going to come forward. So 1 by 2 into 6 is nothing but 3 dB. So therefore this point always you have to keep in your mind. Just 20 log 2 base 10. If you remember this one, you can easily solve this one root 2 also. So 20 log 2 base 10 is always equal to 6 dB. So this formula always you have to this number, because in examinations they are not going to give the calculator. So it is I recommend you to remember these values also. So these are the standard values always you have to keep in mind. So 20 log 2 the base 10 is always equal to 6 dB. So this formula, this number always you have to keep in mind. 20 log 2 the base 10 is always equal to 6 dB. So this number always you have to keep in your mind. So 20 log 2 the base 10 is always equal to 6 dB. 20 log 2 the base 10 is always equal to 6 dB. The next point is the phase margin is equal to tan inverse of 2 zeta by under root over minus 2 zeta square plus under root over 4 zeta to the power of 4 plus 1. So this formula I have already proved you. I already proved in the previous class only, in the formula session only. So this formula always you have to keep in mind. So phase margin is equal to tan inverse of 2 zeta by under root over minus 2 zeta square plus under root over 4 into the power of 4 plus 1. So this value always you have to keep in mind. So this value always you have to keep in mind. So therefore we can say that we can say simply that the formula, phase margin formula. What is the phase margin formula? Phase margin is equal to tan inverse of 2 zeta by under root over minus 2 zeta square plus under root over 4 zeta to the power of 4 plus 1. So phase margin is equal to tan inverse of 2 zeta by under root over minus 2 zeta square plus under root over 4 into zeta to the power of 4 plus 1. So this value always you have to keep in mind. So finally I can say phase margin is equal to tan inverse of 2 zeta by under root over minus 2 zeta square plus under root over 4 into zeta to the power of 4 plus 1. So this value always you have to keep in mind. So this value always you have to keep in mind. So finally I can say that the phase margin is equal to tan inverse of 2 zeta by under root over minus 2 zeta square plus under root over 4 into zeta to the power of 4 plus 1. So if you remember this formula, you can solve this question in a very fraction of second. So therefore, finally, I can say the phase margin is equal to tan inverse of 2 zeta by under root over minus 2 zeta square plus under root over 4 into zeta to the power of 4 plus 1. The next point is, suppose when zeta is equal to 0, the phase margin is always equal to 0. So if we substitute zeta is equal to 0, if we substitute zeta is equal to 0, all this value we are going to get 0. 0 by 1 we are going to get. So 0 by 1 is nothing but 0. Tan inverse of 0 is nothing but 0 degree. So phase margin is equal to 0 degree. So you can say clearly here. So we can write like this. Phase margin is always the proportional to zeta also you can write. So if we substitute zeta is equal to 0, we are going to get phase margin is equal to 0 degree. Then we are going to get. So this formula always you have to keep in mind. So when the zeta is equal to 0, if we substitute the phase margin value also you are going to get 0 also. And the phase margin is always very proportional to Campbell ratio. The next point is for PID controller. What is the transfer function? PID means the output is the proportional to input, integration of the input, and derivative of the input. then that is called as a PID controller. So whenever the output is proportional to input, integral of the input and derivative of the input, and that is called as a PID controller. So as a transfer function, we can say Kp plus Ki by S plus Kds. So here I am going to get Ki by S. So transfer function is equal to Kp plus Ki by S plus Kds. Because the output is proportional to input, integration of the input and the derivative of the input. So because of this, if after the Laplace transform, we are going to get the transfer function just Kp plus Ki by S plus Kd into S. So this is the overall transfer function that we are going to get for the PID controller. So now the next point is, if the Nyquist plot of the G of S H of S does not enclose -1 plus J0, then the closed loop system is stable. So what I told you, basically, what is the meaning of this one? If the Nyquist plot of the G of S H of S does not enclose -1 plus J0, then the closed loop system is said to be stable. This one I have already told you so many number of times. See, I have already told you, if the Nyquist plot of G of S H of S does not enclose the -1 plus J0, then the closed loop system is also stable. Why it is like this? Why it is like this? Let me tell you. So listen, this is open loop transfer function of G of S H of S. That means the Nyquist plot of G of S H of S is not going to enclose the -1 plus J0. So what is the meaning of this one? And what is the meaning of this one? Simply we can say, for this open loop transfer function, there are no poles in the right half of S plane. So P is equal to 0, P is equal to 0. The open loop transfer function itself is, so, or simply we can go it in the other fashion also. N is equal to P minus J. So in the question they are saying that this Nyquist plot is not going to enclose the -1 plus J0. So therefore we can say N is equal to 0. So P we need to figure out. And also they are given the closed loop system is stable. So Z is equal to 0. So with all this we are going to get P is equal to 0 means the open loop system is also stable and the closed loop system is also stable. So therefore we can say both the open loop system are stable and the closed loop system is also stable. So the point they are given, the Nyquist plot of the G of S H of S does not enclose the -1 plus J0 and the closed loop system is stable, then we have to comment on the open loop stability. So N is equal to P minus Z. See, as the Nyquist plot is not going to enclose the -1 plus J0, so therefore we can say N is equal to 0. And also they are given the closed loop system is stableness and no closed loop poles are going to lie in the axis of S plane. So Z is also equal to 0. So from this we can say P is equal to 0 means number of open loop poles that present in the axis of S plane is also equal to 0. So therefore the open loop system is also stable. So therefore G of S H of S won't have any pole in the axis of S plane. So open loop system is also stable. So therefore we can say clearly, so we can say the open loop system and the closed loop system both are said to be stable in this case. I already told you, suppose if the open loop system is unstable, the closed loop system can be either stable or it can be either unstable. Suppose if the open loop system is stable, then the closed loop system can be either stable or unstable. This point I have already told you so many number of times. I have already, this formula always have to remember, N is equal to P minus Z, where N indicates the number of encirclements in the G of S H of S plane at -1 comma J0. I already told you, which is N indicates the number of encirclements of the Nyquist plot in the G of S H of S plane at -1 comma J0. Similarly, P indicates the number of open loop poles or the number of poles of G of H of S which are present in the axis of S plane, and Z indicates the number of poles of the characteristic equation or the number of poles of the characteristic equation which are present in the axis of S plane. So this point always will be keep in your mind. N is equal to P minus Z. N indicates the number of encirclements. N indicates the number of encirclements in the number of encirclements of the Nyquist plot in the G of S H of S plane at -1 comma J0. Where P indicates the number of poles of the G of S H of S which are present in the axis of S plane, and Z indicates the number of roots of the characteristic equation which are present in the right half of the S plane. So these things always you have to keep in your mind. So from this we can say both the open loop system is stable as well as the closed loop system is also stable. The next point is zeta is called as the damping ratio. So whenever the zeta is equal to 0 means we say it is an undamped system. If zeta is lying from 0 to 1, we say it is an undamped system. If zeta is equal to 1, we say it is a critical damped system. And zeta greater than 1 means we say it is a overdamped system. So these things I have already told you so many number of times. Then centered. Centered formula I have already told you. Centered means we can say from this point only we are going to draw the asymptotes. And this template may be part of the root locus or it may not be part of the root locus, which is equal to sigma is always going to lie on the real axis, and its point is sigma comma 0 is equal to summation of the real parts of the pole minus the summation of the real parts of the poles of g of h of s minus summation of real parts of the zeros of the g of h of s by number of poles minus number of zeros. Number of poles is number of open loop poles and number of open loop zeros of open loop transfer function g of h of s. Either you can write like this alpha, which is either you can write summation of the poles minus summation of the zeros. You can write like this, right? Number of open loop poles minus number of open loop zeros. Because here, any of summation is, suppose if you have conjugate poles, plus j minus j, they are going to get cancelled. So same thing we are going to get again. So even though you can do in this method and in this method anyhow, you can say the conjugate poles and conjugate zeros are, they are going to get cancelled because plus 2 is small, plus j2 is small, j2 also you are going to get. So based on this we can say summation of poles minus summation of zeros by number of poles minus number of zeros for the open loop transfer function only. From the open loop transfer function only, we are going to take all this calculation. So therefore, summation of open loop poles minus summation of open loop zeros by number of open loop poles minus number of open loop zeros. So this point always you have to keep in your mind. Now the next point is the transfer function of the armature control DC servo motor has only single time constant. This one I already told. Derivation also I already told you. The transfer function of the armature control DC servo motor has a single time constant, and the expression which is the transfer function is expression k by s into ps plus 1. So we can say the order of the system is equal to 1, whereas the order of the system is equal to 1. So basically order of the system is equal to 2, as you can see clearly, and we have only one time constant which is t. So we can say that the transfer function of the armature control DC servo motor has only single time constant, as you can see clearly from this expression, which is k by s into ts plus 1, and the order of the system is equal to 2. So these things you can see clearly from this equation. So therefore we can say that the transfer function of the armature control DC servo motor, which has only single time constant, which is k by s into ps plus 1. So this one always you have to keep in your mind. So finally I can say the transfer function of the armature control DC servo motor has only single time constant, and the expression of the transfer function is k by s into ts plus 1. So therefore we can say the order of the system is equal to 2, and it has only one time constant. The next point is to find the type of the control system, it is preferable that the gain of the feedback element should be unity. So I already told you what is the type of the system. Type of the system is in the open loop transfer function g of h of s. The number of poles which are present at origin is called as the type of the system. So basically, if you want to figure out the type of the control system, always you try to make the gain as 1. So always try to make the gain h of s is equal to 1. Then try to do the g of h of s, and then try to figure out the number of poles which are present at origin, that is called as a type of the system. So in order to find the type of the control system, it is preferable that the gain of the feedback element should be always unity. So therefore we can say, in order to find the type of the control system, it is preferable that the gain of the feedback element should be unity. So this point always you have to keep in mind. So therefore we can say, in order to find the type of the control system, it is preferable that the gain of the feedback element should be unity. So therefore we can say, I already told you what is the type of system is in the open loop transfer function g of h of s. The number of poles which are present at origin is called as the type of the system. So basically, I have already told you, so in order to find the type of system, always try to keep the feedback element gain which is equal to 1, h of s is equal to 1, and then try to do the multiplication of g of h of s, and then try to figure out the number of poles which are present at origin, that is called as the type of the system. So therefore we can say finally, in order to find the type of the control system, it is preferable that the gain of the feedback element should be unity. The next point is, in the output compensation or the feedback compensation, steady state actuating error affects the dynamics of the plant in order to achieve the control objective. In the output compensation or the feedback compensation, steady state actuating error affects the dynamics of the plant in order to achieve the control objective. So basically, suppose whenever there is a feedback from output to input, so always we try to want the output to be desired output. So because of the feedback, there is going to feedback to the input of the controller, and the controller is going to give the it is going to give the we can say actuating signal in such a way to the plant in order to make the output as is equal to desired output. So listen carefully, in the output composition or the feedback composition, there is a feedback from output to input. So because of this, there is a somewhat error between the actual output and the feedback and the desired output. So this steady state error, we are going to give input to the controller. Then the controller is going to give some actuating signal to the plant in order to make the actual output as a desired output. So therefore we can say in the output compensation or the feedback compensation, steady state actuating error affects the dynamics of the plant in order to achieve the control objective. So therefore the steady state error only, we are going to affect the dynamics of the plant of the system in order to achieve the control objective, which is actual output should be always equal to the desired output. So therefore, finally, I can say this point this point always you have to keep in your mind, which is we can say in the case of output compensation or the feedback compensation, the steady state actuating error is going to affect the dynamics of the plant in order to achieve the control objective. So finally, I can say in the case of output compensation or the feedback compensation, the steady state actuating error is going to affect the dynamics of the plant in order to achieve the control objective. The next point is a potentiometer is a variable resistive displacement transducer which is used as the error detector in the control system applications. A potentiometer is a variable resistive displacement transducer which is used as the error detector in the control system applications. A potentiometer is a variable resistive displacement transducer which is used as the error detected in the control system applications. Basically, I have already told you potentiometer means there will be a huge amount of resistive part. On the resistive part, we are going displacement the resistive part in order to control the output voltage. This I have already told you. So therefore, we can say a potentiometer is a variable resistive displacement transducer which is used as the error detector in the control system applications because the input is a displacement and the output is a voltage. So we are going to convert a physical quantity to electrical quantity. So we say it is a transducer. So therefore we can say a potentiometer is basically a variable resistive displacement transducer which is basically used as the error detector in the control system applications. So this potentiometer we are going to use as the error detector in the case of the control system applications. So finally I can say a potentiometer is basically a variable resistive displacement transducer which is basically used as the error detector in the control system applications. So finally I can say that a potentiometer is a variable resistive displacement transducer which is basically used as the error detector in the case of control system applications because the input is displacement and the output is a voltage. So this is basically used as the error detector in the case of the control system applications. The next point is a pair of potentiometers act as the error detector. So a pair of potentiometers, they are going to act like a error detector. So we can say a pair of potentiometers, they are going to act like a error detector. So a pair of potentiometers, basically they are going to act like a error detector. Always remember, always we are going to use the potentiometers as the error detectors in the case of the control systems. So always we are going to use the potentiometers as the error detector in the case of the control systems. So we can say always we are going to use the potentiometers as the error detector in the case of the control systems. So we are going to use the potentiometers as the error detector in the case of the control systems. So we are going to use the potentiometers as the error detector in the case of the control systems. The next point is tachometers are basically speed transducers and these are used as the feedback elements in the case of the control systems. Tachometers are basically speed transducers and these are used as a feedback element in the control systems. The tachometer means the input is the mechanical speed and the output is the voltage, DC voltage. So basically these are going to control the speed of the motors. They are going to limit the speed of the motors and these are basically used as the feedback elements in the case of the control systems. So we can say the tachometer is basically it is a transducer because the input is the mechanical speed or rotational speed and the output we are going to get the DC voltage. So we are going to convert the physical quantity to electrical quantity. So we say it is a transducer. So basically it is going to limit the speed of the motor. It is going to limit the speed of the motor and it is basically used as a feedback element in the case of the control systems. So finally I can say tachometers are basically speed transducers and these are basically used as the feedback elements in the case of the control systems. The next point is most of the control systems are designed for zeta less than 1 and the optimum values in the case of control system design for a zeta is in the range from 0.3 to 0.8. So basically most of the control systems in the industrial they are designed for the damping ratio less than 1 and the optimum values in the control system design for a zeta is in the range 0.3 to 0.8. So basically I can say most of the control systems in the case of the industries they are designed for the damping ratio which is lesser than 1 and the most optimum values in the case of the control system design is for the zeta is in the range 0.3 to 0.8. So we can say that the optimum value of zeta in the control system is from 0.3 to 0.8. So we can say most of the control systems are basically designed for the damping ratio lesser than 1 and the optimum values in the case of control system design for zeta is in the range from 0.3 to 0.8. So finally I can say that the most of the control systems are basically designed for the damping ratio lesser than 1 and the optimum values in the case of control system design is for the zeta is in the range from 0.3 to 0.8. So finally I can say in simple words, most of the control systems which are designed in the industrial purpose are having a zeta value which is lesser than 1. And if you want to know what is the optimum values of zeta is in the range from 0.3 to 0.8 for design in the case of control systems. The next point is when zeta is equal to 1, the response has no overshoot with minimum settling time. As I already told you, we can say whenever the zeta is equal to 1, we say it is a critical damp system. So critical damp system means it will have minimum settling time. So whether you compare the undamped case or undamped case or overdamped case, out of these only the critical damped case is going to have the minimum settling time. Means within less time the response is going to reach the steady state value. Therefore we can say that when zeta is equal to 1, the response has no overshoot with the minimum settling time. So these things always you have to keep in your mind. So I already told you the formula. What is the peak overshoot? Peak overshoot formula, MP is equal to, so MP is equal to e to the power of minus zeta pi by under 2 or 1 minus zeta square. Suppose zeta is equal to 1, then what is going to happen? E to the power of minus 1 by 0. 1 by 0 is nothing but infinity. So e to the power of y simply means 1 by e to the power of infinity. It is equal to 0. So you can see it clearly from this picture also. So therefore peak overshoot is equal to 0 whenever the value of the zeta is equal to 1. So we can say when zeta is equal to 1, the response has no overshoot with minimum settling time. So therefore we can say when zeta is equal to 1, the response has no overshoot with the minimum settling time. So finally I can say when zeta is equal to 1, the response has no overshoot with the minimum settling time. So finally I can say whether you are going to compare the undamped case or undamped case or over the overdamped case, out of this the critical damped case is going to have the minimum settling time with no overshoot. So this one I have already told you. The next point is a system with transients dying out fastly than other is relatively more stable than other. So basically suppose whenever you are going to compare two systems, for the first system the transients are dying very faster, but for the second system the transients are dying very slower. So from these things we can say the first one is more stable when compared to second one, because for whichever the system trends the dying very more fast, that is said to be more stable. A system with the transients dying more faster than other is relatively more stable than the other. So we can say a system with the transients dying more faster than other is relatively more stable than the other. So therefore we can say a system with the transients dying more faster than other is relatively more stable than the other. So I already told you, suppose in the case of control system, in the pole zero plot, if the poles are going to lie very far away from origin, then their channels are going to die very faster, and we are going to get a more stable system. But if the poles are very closer to origin, then the transients will take a lot of time in order to die out, or we can say these are less stable. So we can say in significant poles, their transients are going to die very faster and they are setting very stable. For dominant poles, their transients are going to die very slower, and we can say this is going to be less stable. So finally I can say a system with transients dying out faster than other is said to be relatively more stable than other. In simple case we can say for whichever the system of transients are dying very faster, that system is more stable when compared to other one. The next point is, for a critically damped system, there is no overshoot and setting time is minimum compared to overdamped systems and underdamped systems. This point I already told you, for a critical damped system, theta is equal to 1. There is no peak overshoot, so peak overshoot is equal to 0, and also the setting time is also minimum. This compared to overdamped case as well as the underdamped case. So this point always you have to keep in your mind. So therefore we can say that for critical damped system, which is theta is equal to 1, there is no overshoot as well as the setting time is minimum as compared to the overdamped case as well as the underdamped case. So this point always you have to keep in your mind. So therefore we can say for critical damped systems, there is no overshoot and the setting time is minimum compared to overdamped systems as well as the underdamped system. So finally I can say for critical damped system, theta is equal to 1, the peak overshoot is equal to 0 means there is no peak overshoot, and the setting time is also minimum when compared to overdamped case as well as the undamped case. So the theta is equal to 0 means it is called as the undamped case means the overshoots are going to present for all the time. When theta value lying from 0 to 1, we say it is a undamped case means as time goes on, the overshoots are going to decrease. So theta is equal to 1 means we can say it is a critical damped system. So in the case of critical damped system, there are no peak overshoots, and the setting time is also minimum when compared to all the remaining three cases. Whereas for the overdamped case, when theta greater than 1, here there will be no peak overshoot, but the response is very sluggish in nature. Plus the setting time is very more. It will take more amount of time in order to settle the output. So these things always you have to keep in your mind. The next point is, when the system has the finite steady state error, then that system is by default stable. So when a system is having a finite steady state error, then by default we can say that system is said to be stable. So whenever the system is having a finite steady state error, then by default we can say the system is said to be stable. So we can say whenever the system is having a finite steady state error, then that system is default it is said to be stable. So whenever the system is having a finite steady state error, then by default we can say that system is said to be stable. So basically we can say, see, whenever any system which is having a finite steady state error or zero steady state error, we can say it is said to be a stable system. But if the steady state error increases as time goes, means we can say it is an unstable system because it is an unbounded output. I already told you whenever the output is bounded, we can say it is a stable system, but if the output is unbounded, means we can say it is an unstable system. So therefore we can say, based on this we can say whenever the system is having a finite steady state error, it indicates that the output is always bounded. So therefore we can say the system is said to be stable. But if the system is having the varying increasing steady state error as time goes on, then we can say the output is unbounded. So therefore we can say the system is said to be unstable. The next point is, output rate control is basically used to improve the damping of the system. So output rate control is basically used to improve the damping of the system. I've already told you output rate control means the feedback control. So with the help of feedback, we are going to improve the damping of the system. Improving the damping of the system is theta increases because as theta increases, the oscillations are going to decrease in a very less amount of time. So therefore, we can say that the oscillations are going to reduce in a small amount of time. So that is called as the output rate control. So with the help of output rate control or with the help of feedback control, we are basically going to improve the damping of the system. So therefore, we can say with the help of output rate control or with the help of feedback control, we are basically improving the damping of the system. So with the help of the output rate control or the feedback control, we are going to improve the damping of the system. Improving the damping of the system means the damping ratio is going to get increases. So therefore, we can say output rate control is basically it is used to improve the damping of the system. So output rate control is basically it is used to improve the damping of the system. I've already told you output rate control means the feedback control. With the help of feedback control, we are going to improve the damping of the system. Means to improve the damping of the system means theta increases. So therefore, the peak core should decreases because theta is inversely proportional to peak core should. As theta increases, peak core should decreases. So the oscillations are going to get reduced in a less amount of time. And the time constant, the settling time for the 5% steady state error, which is equal to 3 by zeta omega n. As zeta increases, so therefore we can say that the settling time is also going to get decreases. So these things you can see clearly from this expression also. So therefore finally I can say in the case of output rate control or the feedback control, we are going to improve the damping of the system is the theta is going to get increases. So when theta increases, the settling time is going to get decreases. As you can see clearly from this expression, the settling time for the 5% steady state error is equal to 3 by zeta omega n. As theta increases, the settling time is going to get decreases. Improve the damping ratio means the zeta value is going to get increases. The next point is process industry applications should ideally be tuned for the critical damped because critical damped response has no oscillations in the output. Process industry applications should ideally be tuned for the critical damped because critical damped response has no oscillations in the output. So basically we can say the process industry applications should ideally be tuned for the critical damped because the critical damped response has no oscillations in the output. So basically we can say the process industry application should ideally be tuned for the critical damped because critical damped response has no oscillations in the output. So basically in the process industry applications, we ideally make the systems designed for the critical damped because in the case of critical damped response, there will be no oscillations in the output and also the settling time is also minimum. So because of these reasons only, we are going to design in the case of process industry applications, always we are going to design the systems for the critical damped response. So in the case of process industry applications, always we try to design the systems with the critical damped response. So therefore, the critical damped response means theta is equal to 1. So there will be no oscillations in the output and within the minimum time you are going to get the response. So finally I can say the process industry applications should ideally be tuned for the critical damped because critical damped response has no oscillations in the output. So therefore we can say the process industry applications should ideally be tuned for the critical damped because the critical damped response has no oscillations in the output. So finally I can say that the process industry applications should ideally be tuned for the critical damped because the critical damped response has no oscillations in the output. So finally I can say in simple words that in the case of process industry applications, always we are going to design the control systems in order to have the critical damped response in the output. So because of this, there will be no oscillations in the output and also we can say with the minimum certain time, the output is going to reach the steady state value. So because of these advantages only, always we are going to design the process industry applications with the critical damped response. The next point is a unit impulse response of a second-order system is given by. A unit impulse response of a second-order system is given by. So basically for a second-order system, we can say what is the standard transfer function, which is omega n square by s square plus 2 zeta omega ns plus omega n square. So for this closed loop transfer function, if you give the input as delta of t, which is r of s is equal to 1, then what is the c of s, which is equal to the, if we the input delta of t, the output is h of t, so we can say this h of s. So if we try to figure out the Laplace inverse of h of s, then we are going to get h of t. That response is k into e to the power of minus zeta omega n t by under root over 1 by zeta square sine of omega d plus phi. So phi is nothing but cos inverse of zeta. Phi is equal to cos inverse of zeta. So this one always you have to keep in your mind. Where phi is equal to cos inverse of zeta. So this one always you have to keep in your mind. So phi is equal to cos inverse of zeta. So therefore we can say for a unit impulse response of a second order system is given by h of t is equal to k into e to the power of minus zeta omega n t by under root over 1 by zeta square sine of omega t plus phi. So we can say the impulse response of a second order system, which is given by h of t is equal to k into e to the power of minus zeta omega n t by under root over 1 by zeta square sine of omega t plus phi. So this point always you have to keep in your mind. So I already told you what is the standard transfer function of the signal system is omega n square by s plus 2 zeta omega ns plus omega n square. For this, if you are going to be the input as delta of t, and what is the expression of the h of t, which is equal to k into e to the power of minus zeta omega n t by under root over 1 minus zeta square sine of omega d t plus phi. So this point always you have to keep in your mind. So finally I can say the unit impulse response of a second order system is given by h of t is equal to k into e to the power of minus zeta omega n t by under root over 1 by zeta square sine of omega d t plus phi. So finally I can say the unit impulse response of a second order system is given by h of t is equal to k into e to the power of minus zeta omega n t by under root over 1 by zeta square sine of omega d t plus phi. The next point is Kp is called as the positional error constant and Kb is called as the velocity error constant and Ka is called as the acceleration error constant. Or coefficient also we can say whether it's the constant or coefficient, we can call it anything. So Kp is called as the positional error constant, Kb is called as the velocity error constant, whereas the Ka is called as the acceleration error constant. So these things always you have to keep in your mind. So Kp is called as a positional error coefficient, whereas the Kv is called as a velocity error coefficient, whereas the K is called as the acceleration error coefficient. So these points always you have to keep in your mind. So therefore finally I can say Kp is called as a positional error constant, Kv is called as a velocity error constant, and K is called as the acceleration error constant. So Kp is nothing but a limit s tends to 0 g of s into h of s. Whereas Kv is equal to limit s tends to 0 s into g of s into h of s. Whereas K is equal to limit s tends to 0 s square into g of s into h of s. So these things always you have to keep in your mind. So therefore we can say Kb is called as a positional constant and its value is equal to limit s tends to 0 g of s h of s. Whereas Kv is called as a velocity error constant, coefficient or constant, its value is equal to limit s tends to 0 s into g of s h of s. Whereas K is called as the acceleration error constant and its value is equal to limit s tends to 0 s square into g of s h of s. The next point is transfer function approach is inadequate when time domain solution is required because all initial conditions of the system are neglected in derivation of the transfer function. Transfer function approach is inadequate when time domain solution is required because all the initial conditions of the system are neglected in derivation of the transfer function. As I've already told you, whenever we are going to derive the transfer function of a given system, definitely we are going to assume all the initial conditions. Then if you try to figure out the time domain response, definitely we can say here the response is not going to include any past values. Past values always we are going to assume its value is equal to 0. We can say this inadequate means it is not giving the full information of the output for all the time. So therefore we can say while deriving the transfer function of a system, we are going to assume the initial conditions are 0. So based on this we are going to get the output. So for this output, if you try to figure the time domain response of this output, So this output is not going to give the information of each and everything because we have already assumed the initial conditions of 0. So we can say this is inadequate result. Means it is not 100% correct equation. So finally I can say the transfer function approach is inadequate when time domain solution is required because all the initial conditions of the system are negated in the case of the derivation of the transfer function. So we can say the transfer function approach is inadequate when time domain solution is required because all the initial conditions of the system are negated in the derivation of the transfer function. So finally I can say that the transfer function approach is basically inadequate when time domain solution is required because all the initial conditions of the system are negated in derivation of the transfer function. So finally I can say that in simple words, whenever we are going to get the transfer function of a system, we are going to assume the initial conditions are 0. So based on this, we are going to get the, with the help of Laplace inverse transform, we are going to get time domain response of the output. And here, it is time domain response of the output. It is not going to give the exact result of the output for all time. So because the initial conditions are assumed, we have 0. So based on this, we can say this is not a perfect result, or we can say this is the inadequate result. So the next point is, which is S of t is equal to integration of 0 to t h of t dt. When h of t is called as the impulse response and s of t is called as the step response, then h of 0 can be anything. So basically, if you see clearly, I've already told you the step signal. The step signal is the integration of the we can say impulse signal. So similarly, the response also going to follow the same thing. So u of t responses. So whenever you are going to give u of t as a input to a system, the output is s of t. Similarly, whenever you are going to give the input as delta of t, the output is h of t. So therefore, same thing. For u of t, the output is h of t. For delta of t, the output is h of t. For u of t, the output is s of t. And for delta of t, the output is h of t. So both will have the same amount of relation. So therefore, we can say that the step signal is the integration of the impulse signal, or vice versa, which is vice versa. What is the result? Delta of t is the integration of the step signal. So delta of t is equal to differentiation of the step signal. Similarly, u of t. Similarly, the response is also going to follow the same thing, which is h of t is equal to d by dt of s of t. So this one always you have to keep in your mind. So these two things always you have to keep in your mind. Definitely, you are going to come across this one. Suppose I am going to assume h of t is 0 from minus infinity to 0. So therefore, the integration is going to become now integration from 0 to t, h of t dt. As you can see clearly, we have assumed the value of h of t from minus infinity to 0. Its value is 0, we have assumed. So based on this, we can say that the integration is now going to simplify from 0 to t. So this point you can see clearly from this one. So the next point is zeta is called as the damping ratio or the damping factor or the damping constant. So basically zeta is called as the damping ratio or the damping factor or the damping constant. So basically zeta is called as the damping ratio or the damping constant or the damping factor. So zeta is called as the damping ratio or the damping factor or the damping constant. So this one I've already told you so many number of times. So zeta is called as the damping ratio or the damping factor or the damping constant. Zeta is equal to 0 means undamped system. Zeta lies from 0 to 1 is called as the undamped system. Whereas zeta is equal to 1 means it is called the critical damped system. And zeta greater than 1 is called as the overdamped system. So finally I can say zeta is called as the damping ratio or the damping factor or the damping constant. Whenever zeta is equal to 0 means it is called as the undamped system. Zeta lying from 0 to 1 is called as the undamped system. And zeta is equal to 1, it is called as the critical damped system. And zeta greater than 1 is called as the overdamped system. The next point is, in the time domain specification, the decay ratio is the ratio of the amplitude of the first two successive peaks. So we can say, in a time domain specification, decay ratio is the ratio of the amplitude of the first two successive peaks. So basically, you know the response, right? So this is the response nature. So you are going to get, this is the response nature you are going to get. So basically, these two peak values. So these two peak values, we are going to do the ratio. So let me assume this is x1 and this is x2. So this is this peak value by this peak value. The ratio, it is called as the decay ratio. So x1 by x2 is called as the This is called as decay ratio. In time domain specification, decay ratio is the ratio of the amplitude of the first two successive peaks. So therefore, we can say in simple words, in the case of time domain specifications, the decay ratio is the ratio of the amplitude of the first two successive peaks. So therefore, we can say in the case of time domain specifications, the decay ratio is the ratio of the amplitude of the first two successive peaks. So finally, I can say in the case of time domain specifications, the decay ratio is the ratio of the amplitude of the first two successive peaks. So if you see the graph, you are going to get the output in this manner. So this is the first overshoot and this is the first undershoot. Or you can say this is the first, so this is the first undershoot, first overshoot, and this is the second overshoot. So listen, this is the first overshoot and this is the second overshoot. So x1 is the peak of the first overshoot and x2 is the peak of the second overshoot. So first overshoot, first undershoot, second overshoot, second undershoot, and goes on. So therefore we can say it is a ratio of the peaks of the two successive peaks is called as the we can say so in time domain specification the decay ratio is the ratio of the amplitude of the first two successive peaks, which is x1 is the peak value of the first overshoot and x2 is the peak value of the second overshoot. So these two ratios we are going to call as a decay ratio. So finally I can say the time domain specification the decay ratio is the ratio of the amplitude of the first two successive peaks. So this point always you have to keep in your mind. We are going to discuss the another important point. Listen carefully. The phase rate compensation improves the transient response. It indicates that the rise time is going to get decreases, bandwidth is going to get increases, and the steady state error is going to get increases. As I've already told you one important point. In the case of phase rate compensation, it is always going to improve only the transient response and it is going to deviate the steady state response to a small amount of extent. This one I've already told you so many number of times. So therefore we can say the phase rate compensation is going to improve the transient response, whereas it is going to deviate the steady state response to a small amount of extent. Improving the transient response means the rise time is going to get decreases. So therefore the speed of the response will be very, very high. And you know already the rise time into bandwidth is always equal to constant. As the rise time decreases, so definitely bandwidth must increase. Then the part is equal to constant. And I've already told you it is going to deviate the steady state error. So therefore the steady state error will increase. And also we can say the gain crossover frequency is also going to get improves. I've already told you this point always you have to keep in your mind, which is the gain crossover frequency is also going to get increases. So these things always you have to keep in your mind. In the case of phase rate compensation, we can say 0 is very closer to origin and compared to pole. This one also I have already told you. So now the next one is by adding a pole, the order of the denominator increases. Then what is going to happen? Which is the P quotient is going to get increases, the rise time is going to get increases, the stability is going to get decreases, and the bandwidth is going to get decreases. Why it is like this? See, adding a pole means I've already told it is a PI controller, or we can say lag compensator. Adding 0 means phase rate compensator. Adding pole means we can say PI controller, or basically we can say it is a lag compensator. So by adding a pole, we can say it is a lag compensator. So whenever you are going to add a pole, definitely the order is going to get increased by 1 unit, as well as time is also going to get increased by 1 unit. So therefore we can say the order of the denominator increases, as well as the type of the typo system is also going to increase by 1 unit. Then what is going to happen? As I already told you, this is a lag compensator. So in the case of lag compensator, it is always going to improve the steady state response. So it is going to deviate the transient response to a smaller amount of extent. So therefore we can say the steady state error will be 0 here. So steady state error will be 0. So as the rise time is going to get increases, as you can already see here, but bandwidth is going to get decreases because the part is always equal to constant. And I've already told you one important point. In all the three cases, the damping ratio is going to get increases. Here also damping ratio increases, here also damping ratio increases. So whenever damping ratio increases, the P quotient will decrease. So here listen carefully, the P quotient will decrease. So here the P quotient is increasing. So this is the point always you have to keep in mind. So I hope here basically it's a vice versa. A small correction here. actually the damping ratio will decrease here. So small correction here, the damping ratio will decrease, whereas here the damping ratio is going to get increases. So here in the previous case, we can say here the damping ratio is going to get increases, here the damping ratio is going to get decreased. So this point always you have to keep in your mind. So therefore we can say here the damping ratio is going to get decreases. So whenever the damping ratio decreases, we can say the P quotient is going to get increases. So both are inversely proportional. So whenever you are going to add a pole, the stability is going to get decreases, but here the stability is going to get increases because we are adding a 0. So these things always you have to keep in your mind. So whenever you are adding a 0, the stability increases. Whenever you are adding a pole, the stability will decrease. So these things always you have to keep in your mind. The next point is, for a minimum phase transfer function, all the zeros and the poles must always lie on the edges of the S-plane only. See, I have already told you, for the minimum phase transfer function, all the zeros as well as the poles should always lie on the edges of the S-plane only. I have already told this important point. For a minimum phase transfer function, all the zeros as well as the poles, they always must lie only on the LHS of the S-plane only. So we can say, for a minimum phase transfer function, all the zeros as well as the poles must always lie only on the LHS of the S-plane itself. The next point is, for non-minimum phase transfer function, all the zeros lie on the LHS of S-plane and all the poles lie on the LHS of S-plane only. So this point always you have to keep in your mind. For non-minimum phase transfer function, all the zeros, they are going to lie on the LHS of the S-plane, whereas all the poles are going to lie in the LHS of S-plane only. So this one always you have to keep in your mind. So this one I already told you so many number of times. In the case of minimum phase transfer function, all the zeros as well as the poles, they must lie always only on the LHS of the S-plane. Whereas for the non-minimum phase transfer function, all the zeros should lie on the LHS of S-plane, whereas all the poles should lie on the LHS of S-plane. So these point always you have to keep in your mind. So we can say, for a minimum phase transfer function, all the zeros and the poles should always lie only on the LHS of the S-plane, whereas for the non-minimum phase transfer function, all the zeros should lie on the LHS of S-plane, whereas all the poles should lie only on the LHS of S-plane. So this should always you have to keep in your mind. So finally, I can say, for a minimum phase transfer function, all the zeros and the poles should lie only on the LHS of S-plane, whereas for non-minimum phase transfer function, all the zeros should lie on the LHS of S-plane, whereas all the poles should lie on the LHS of S-plane only. So this point always you have to keep in your mind. The next point is, when all the elements in one row of the Raoult's tabulation are 0, then it means. See, basically, when all the elements in one row of the Raoult's tabulation are 0, then what is going to get indicated? Suppose, when all the elements in one row of the Raoult's tabulation are 0, then it is going to indicate what is that thing. Listen carefully. When all the elements in one row of the Raoult's tabulation are 0, then what is going to get included? We need to figure out. See, I have already told you, whenever one complete row is 0 in the case of RH table, it indicates that. Then you have to take the above equation of the other equation and do the differentiation of this one in order to write the coefficients in place of zeros, and then you have to proceed in order to figure out the remaining values of the tabulation. But if it is 0 means what is that? It is going to indicate, which is one pair of real roots with the opposite side in the S-plane, or one pair of conjugate roots on the imaginary axis in the S-plane, or conjugate roots forming a quadrature in the S-plane. So this point I have already told you. You can get any 3 cases. So what is the 3 cases? So you can see clearly. So this is one case. This is one case, and the other case is this one, and the other case is this one. So these are the 3 cases. So out of this, one is the case by which we are going to get this one, maybe this one. So therefore, you can say when all the elements in one row of the Raoult's tabulation are 0, then it means that one pair of the real roots with opposite side in the S-plane, one pair of conjugate roots on the imaginary axis in S-plane, conjugate roots forming the quadrature in the case of the S-plane. So these things always you have to keep in your mind. So therefore, you can say when all the elements in one row of the Raoult's tabulation are 0, then it is going to indicate that one pair of real roots with the opposite side in the S-plane, one pair of conjugate roots on the imaginary axis in the S-plane, conjugate roots forming a quadrature in the S-plane. So this point always you have to keep in your mind. So finally, I can say when all the elements in one row of the rows tabulation are 0, then it is going to indicate that one pair of real roots with opposite sign in the S-plane, one pair of conjugate roots on the imaginary axis of the S-plane, and the conjugate roots forming a quadrature in the S-plane. So these things always you have to keep in your mind. So finally, I can say when all the elements in one row of the roots tabulation are 0, then it indicates that there is a one pair of roots with the opposite side in the S-plane and one pair of conjugate roots on the imaginary axis in the S-plane and conjugate roots forming a quadrature in the S-plane. So out of this one case is possible because of this only, this is the only one row is completely 0 in the case of RH table. The next point is all the coefficients of the calistic equation should be positive and no term should be missing in the calistic equation for a system to be stable. Because if some of the coefficients are 0 or negative, then the system is not stable. This point I have already told you. See, whenever by seeing the calistic equation, you can say whether it is stable or not. Suppose if there is no sign change, and not even any term is missing, then we have to do the further analysis to comment on the stability. But if any term is missing, or if there is any sign change in the calistic equation, by default we can say it is said to be unstable. All the coefficients of the calistic equation should be positive and no term should be missing in the calistic equation for the system to be stable. Because if some of the coefficients are 0 or negative, then the system is not stable. I have already told this important point. Suppose whenever you take a calistic equation, suppose if there is any missing term or if there is any sign change in the calistic equation, by default we can say that it is said to be unstable system. But if there is no sign change, if there is no term missing, then we have to do further analysis in order to comment on the stability. So this point always you have to keep in mind. So finally I can say, so by seeing the calistic equation, if there is any sign change or if there is any term missing, by default we can say it is said to be unstable system. But if there is no sign change, if there is no term missing, then we have to do further analysis in order to comment on the stability. The next point is zeta is called as the damping ratio or the damping factor or the damping constant or the damping coefficient. These are the different names for the zeta. So zeta is called as the damping ratio or the damping factor or the damping constant or the damping coefficient. These are the different names for the damping ratio zeta. So we can say the different names of the zeta, it is damping ratio or the damping factor or the damping constant or the damping coefficient. These are the different names for the zeta. So therefore finally I can say zeta is called as the damping ratio or the damping factor or the damping constant or the damping coefficient. These are the different names for the zeta. So finally I can say zeta is called as damping ratio or the damping factor or the damping constant or the damping coefficient. So zeta is equal to 0 means it is called as the undamped system. If zeta is lying from 0 to 1, it is called as the underdamped system. If zeta is equal to 1, it is called as the critical damped system. If zeta is greater than 1, it is called as the overdamped system. So finally listen carefully. If zeta is equal to 0 means it is called as the undamped system. If zeta is lying from 0 to 1, it is called as the underdamped system. If zeta is equal to 1, it is called as the critical damped system. And if zeta is greater than 1, it is called as the overdamped system. So these things always you have to keep in your mind. The next point is, if the damping ratio is negative, then that system is perfectly unstable. So whenever the damping ratio is negative, we can say that system is perfectly unstable. As I have already told you, whenever the damping ratio is positive, we say it is a stable system. But if you are going to get the damping ratio as negative with the help of calculation, we can say by default it is said to be unstable system. So if the damping ratio of the system is negative, by default we can say it is said to be unstable system. And I have already told you, whenever zeta value is equal to 0 means it is called as an undamped system. If zeta is lies from 0 to 1, it is called as an undamped system. And zeta is equal to 1 means it is called the critical damped system. And zeta greater than 1 is called as the overdamped system. So these parts are already told you several number of times. So therefore, we can say that whenever the damping ratio of the system is positive, we say it is stable system. But if the damping ratio of the system is negative, we say the system is said to be perfectly unstable system. The next point is C of S by R of S is a transfer function. C of S is the Laplace transform of output signal. R of S is the Laplace transform of input signal. So in the ratio, we are going to the transfer function. And in this transfer function, if substitute is equal to 0, we are going to get the DC gain of the open loop control system. So we are going to get the DC gain of the open loop control system. See, basically, this is the open loop system. That is the reason we are going to get the DC gain of the open loop control system. Suppose this is the closed loop transfer function, then we are going to get the DC gain of the closed loop control system. So this point always you have to keep in your mind. So if you are taking the open loop system, if you are taking the transfer function of the open loop system, and if the substitute is equal to 0, we are going to get the DC gain of the open loop control system. But if you take a closed loop control system and if the substitute is equal to 0, we are going to get the DC gain of the closed loop control system. So this one always you have to keep in your mind. So you can say, whenever you are taking the open loop transfer function and if the substitute is equal to 0, then we are going to get the DC gain of the open loop control system. But if you take the closed loop control system and if the substitute is equal to 0, we are going to get the DC gain of the closed loop control system. So this one always you have to keep in your mind. So finally I can say, if you are taking the open loop transfer function and if the substitute is equal to 0, we are going to get the DC gain of the open loop control system. But if you take the closed loop transfer function and if the substitute is equal to 0, we are going to get the DC gain of the closed loop control system. The next point is, the maximum peak quotient is always inversely proportional to zeta. This one I already told you. Because you can see clearly what is the relation between MP and zeta. The MP is equal to e to the power of minus zeta pi by under root over 1 minus zeta square. So both are inversely proportional. As zeta increases, the EMP is going to get decreases. So P quotient is going to get decreases. So therefore we can say EMP is inversely proportional to zeta. The system with least zeta has more overshoot. So definitely we can say the system with least zeta means zeta is equal to 0, then we are going to get the maximum overshoot. If zeta is equal to 0, then we are going to get what is the value with the power of minus 0, which is equal to 1 by the power of 0. It is nothing but 1, so 100%. Therefore we can say the less is the value of zeta, more is the peak overshoot. So we can say simple words like that. So less is the zeta means we are going to get the maximum overshoot or highest value of peak overshoot. So finally I can say MP is the peak overshoot and the relation is MP is equal to the power of minus zeta pi by under root over 1 minus zeta square, or simply we can say MP is inversely proportional to zeta. As zeta increases, MP decreases. So the least value of zeta, we are going to get the maximum value of the peak overshoot. So therefore least value of zeta is going to give you the maximum value of the peak overshoot. So therefore the system with least zeta will have the more amount of overshoot. So this one always you have to keep in your mind. The next point is, if the poles lie on the imaginary axis or at the origin, then the output may be bonded or unbonded for a bonded input. Listen carefully. If the poles lie on the imaginary axis or at the origin, then the output may be bonded or unbonded for a bonded input. So this one I already told you. Suppose if the poles are going to lie on the LHS of the S-plane, they may be repeating or they may be repeating or non-repeating. Always we are going to get a response with a decaying. We can say the impulse response will be decaying. It will be decaying as time goes on. We can say the impulse response is going to tend to 0 as t tends to infinity. Suppose if the poles are going to present on the imaginary axis and they are not repeating, then what is the thing we are going to get? Then what is the thing that we are going to get is basically the impulse response will have a finite value as t tends to infinity. So therefore we can say this is a marginally stable system. Suppose if the poles on the imaginary axis if they are repeating, then in that case the impulse response tends to infinity as t tends to infinity. So we say it is an unstable system. But if the poles are going to lie in the axis of S-plane, whether they are repeating, whether they are not repeating, by default we can this system is said to be unstable system. So these things always you have to keep in your mind. So whenever the poles which are lying on the imaginary axis or at the origin and they are not repeating, suppose they are not repeating. Suppose if they are not repeating means bonded up, you are going to get a bond output. So if they are repeating means we are going to get unbonded output. So therefore we can say finally, I have already told you, whenever the poles are going to lie on the imaginary axis If they are not repeating means output we are going to get bounded. Suppose if they are not repeating means we are going to bound output. If they are going to repeat means we are going to get the unbounded output for a bounded input. This one always you have to keep in mind. So the next point is, suppose k value is lying from -1 to +1. We can write in another fashion which is mod of k is less than 1. We can write in this fashion. Mod of we can say equivalent way of writing. So -1 less than k less than or equal to 1. Simply we can say this mod k less than 1. It can get like this. So it's a shortcut way of writing. So therefore we can say now the k lies from -1 to +1. We can write like this, which is mod k less than 1. We can write like this way. Anyway, it is going to represent the same thing. The next point is, when all the elements of a row in a row house array ends up abruptly, that is, all the elements of the row have a 0 values, then the system will be either unstable or marginally stable. Marginally stable means it will have imaginary roots. Two equal and opposite complex roots on the imaginary axis of the S-plane. So listen carefully. When all the elements of a row in the Routh-Harvard array ends up abruptly in all the elements of the row have a 0 values, then the system will be either unstable or marginally stable. Marginally stable means it will have imaginary roots, two equal and opposite complex roots on the imaginary axis of the S-plane. So what I am trying to tell you, suppose I already told you, when all the elements of a row in the case of RH array ends up abruptly, or you can say all the elements of the row have 0 values, then the system can be either unstable or marginally stable. Marginally stable means it will have imaginary roots, two equal and opposite complex roots on the imaginary axis of S-plane. So in simple words I can say, suppose in the case of RH table, if one of the row is completely 0, then what is the meaning of this one? Then the above equation is taken as auxiliary equation. With the differentiation of the one, in order to replace these zeros by those conditions and try to figure out the remaining values of the variables. So this I have already told you. So I have already told you, whenever any complete row is 0, it indicates that the roots can be real with equal and opposite sign, or they may be purely complex conjugate, or you can say they are purely imaginary, or you can get a complex roots of 4. Out of these three cases, one case is going to get possible, as I already told you. So the system can be either marginally stable or it can be unstable. Out of this, one is going to happen always. So I already told you how it's like this. So what are the three cases? So this is the case 1. So this is the case 2. So this is the case 3. Out of this, one is going to happen for sure. So now you can see here one. So you can see clearly here in this case, we can say this is said to be unstable system because one pole is also explained. So this is called as the marginal stable system, and this is called as the unstable system. So only two cases are possible, whether unstable system or marginally stable, but there is no completely stable. So definitely out of these two cases, one case is going to happen, which is either system can be unstable or marginally stable. Out of this only one is going to get possible. As you can see clearly, whenever any row is completely 0, it indicates out of these three cases, one case is going to happen. So we can say in the first case, compulsory it is said to be unstable system. In the second case, we can say it is said to be marginally stable system. In the third case, we can say it is said to be unstable system. So therefore, we can say simply the system can be either unstable system or marginally stable system. Out of these two, only one thing is going to happen. So these things always you have to keep in your mind. So the next point is, when the gain margin in dB is positive, then by default we can say the system is said to be always stable. I have already told you this also many number of times, but let me repeat here. So this one, listen carefully. Let me take a characteristic equation. We can say AS2 plus BS2 plus CS plus D is equal to 0. So whenever AD is less than BC, then we can say the system is said to be stable system. And also the gain crossover frequency is lesser than the phase crossover frequency. And also one more thing is the gain crossover frequency is lesser than the phase crossover frequency. And also one more thing is, what is the point? Gain margin and the phase margin both are said to be positive. Gain margin in dB is positive, phase margin in degree which is positive. Suppose if AD is equal to BC, we say it is a marginally stable system, means the gain crossover frequency is equal to phase crossover frequency, and the gain margin in dB and the phase margin in degrees both are said to be at 0. So both are equal and also they are 0. Similarly, in the other case, it is greater than Vc. It is said to be unstable system. So gain cause of frequency is greater than phase cause of frequency. Gain margin as well as the phase margin both are said to be now negative. So gain margin in dB and phase margin in a degree both are said to be negative for unstable system. So this should always be keep in your mind. So whenever the gain margin is positive, we can say it is said to be stable system. The next point is the root locus plot determines the relative stability of the system. Yes, with the help of root locus we can figure out the transient behavior as well as the relative stability of the system. Just by seeing the two root locus we can say which one is more stable and which one is not morely stable, and which is having the less transient time also we can easily figure out just by seeing the root locus. So these things always you have to keep in your mind. So with the help of root locus we can figure out the transient response statistics as well as the stability, relative stability also we can easily compare between the two systems. So we can say finally the root locus is basically basically determine the relative stability of the system. So root locus plot is going to determine the relative stability of the system. So this one always you have to keep in your mind, which is the root locus plot is going to determine the relative stability of the system. So this point always you have to keep in your mind, which is the root locus plot is always going to determine the relative stability of the system. So finally I can say the root locus plot is going to determine the transient response statistics as well as the relative stability of the system. So these things always you have to keep in your mind. The next point is when we add poles, the root locus is going to shift to the arches of the S-plane. So stability is going to get reduces. This point I already told you. So whenever we are going to add the poles, the root locus is going to shift to the arches of the S-plane. So therefore the stability is going to get decreases. So whenever we are going to add the poles to the transfer function, the root locus is going to shift to the arches of the S-plane. So therefore the stability is going to get reduces. But similarly, if we add the zeros to the open transfer function, the root locus is going to shift to the arches of the S-plane. So therefore stability is going to get increases. So these things are already told you so number of times. So finally I can say whenever we are going to add the zeros to the open transfer function, the root locus is going to shift to the arches of the S-plane. So the system is simply more and more stable. But if we add the root locus, if we add the poles to the open transfer function, then the root locus is going to shift to the arches of the S-plane. So therefore the system is said to be unstable. So now the next point is, in order to make the unstable system to be stable or to improve the stability, reduce the gain is the first priority and adding zero is the second priority. As I've already told you, basically if you want to improve the stability of the system or if you want to make an unstable system to stable, first thing that you have to do is to reduce the gain. So reducing the gain is the first priority and adding the zero is the second priority. I already told you how we can improve the stability of the system by decreasing the gain of the system or by adding the zero to the system. So basically this point I have already told you so many number of times. So whenever we are going to decrease the gain of the system stability increases. And whenever you are going to add the zeros to the transfer function, then also the root locus is going to shift to the arches of S-plane. So therefore the system stability is going to increases. So adding zero is the second priority. So finally I can say, in order to make the unstable system to stable or to improve the stability, reducing the gain is the first priority and adding the zeros is the second priority. So finally I can say, in order to make the unstable system to stable or to improve the stability, reducing the gain is the first priority and adding the zeros is the second priority. So finally I can say in simple words, see, whenever you are going to increase the gain, the root locus is going to shift to the arches of the S-plane, so therefore the stability will decrease. If you add the zeros, the root locus is going to shift to the arches of the S-plane, so therefore the system stability will increase. So finally I can say, if you want to improve the stability of the system or if you want to make an unstable system to stable, first thing is you have to reduce the gain of the system, that is the first priority, and adding the zeros is the second priority. So by these two ways we can improve the stability of the system. The next point is root contours or multiple root locus diagrams which are obtained by varying the multiple parameters in a transfer function. Root contours are the multiple root locus diagrams which are obtained by varying the multiple parameters in a transfer function. So basically, this is already told you shown a number of times. Suppose in a open loop transfer function, if you have more than one variable, so by varying each and every variable, we are going to get a corresponding root locus. So if you combine all these things, this is called as the root contours. So root contours are the multiple root locus diagrams which are obtained by varying the multiple parameters in the case of the transfer function. As I've already told you, whenever we take open loop transfer function, we have more than a variable. If we have more than one variable, so vary each variable at one time and remain this keep it fixed state. So with the help of this, we are going to get a root locus diagram. So combination of all these root locus diagrams is called as the root contours. So finally, I can say root contours are the multiple root locus diagrams which are basically obtained by varying the multiple parameters in the case of the transfer function. The next point is if the root locus is IRL, if the root locus is the inverse root locus, then write the g of h of s from it, and it is a positive feedback system. So the closed loop transfer function is g of s by 1 minus g of s h of s. If the root locus is the inverse root locus, then write g of s h of s from it, and it is a positive feedback system. So the closed loop transfer function is g of s by 1 minus g of s h of s. So basically, what are the root locus? Basically, suppose if they are given inverse root locus, then try to figure out the g of s h of s from this inverse root locus, and basically it is a positive feedback system. Root locus means negative feedback system, inverse root locus means positive feedback system. Then what is the closed loop transfer function? G of s by 1 minus g of s h of s. So this formula always you have to keep in your mind. So finally I can say, suppose they are given inverse root locus. So from that, try to figure out the g of s h of s from the inverse root locus. So root locus means positive negative feedback, inverse root locus means positive feedback. And what is the closed loop transfer function, which is g of s by 1 minus g of s h of s. So finally I can say that suppose if they are given the inverse root locus, so from the inverse root locus try to figure out the g of s h of s open loop transfer function. And root locus means negative feedback system, inverse root locus means positive feedback system. So from this try to figure out the closed loop transfer function, which is g of s by 1 minus g of s h of s. So these things always you have to keep in your mind. The next point is the critical dam systems are highly sensitive to noise. So this point I have already told you so many number of times. The critical dam systems are highly sensitive to noise. See, whenever the zeta is equal to 1, we say these are the critical dam systems. For the critical dam systems, there will be no oscillations and the response is going to have the minimum settling time. So in all the case of industrial, always we try to design with the zeta is equal to 1 only, because in the response there will be no oscillations and we will have the minimum settling time. So this is the always we are going to design the applications in industrial to have a critical dam response. So now here basically we can say, so these are also very highly sensitive to noise. Means they can withstand the noise or they can easily eliminate the noise also. Because there are no oscillations. No oscillations means we can say they are very highly so basically we can say they are highly sensitive to noise means we can say they are very highly sensitive means basically we can say they are very highly sensitive to noise. So when zeta is equal to 1 means we can say critical dam. So this critical dam response is very highly sensitive to noise. Highly sensitive means we can say they are very sensitive. Even a small amount of noise can make the system either overdam system or underdam system. A small amount of noise if you give to these critical dam systems, they can become either overdam systems or either they can become the underdam systems. So this point always you have to keep in your mind. So therefore, a small amount of noise for the critical dam systems, it makes the system to become either overdam systems or the underdam systems. So this point always you have to keep in your mind. So finally I can say the critical dam systems are highly sensitive to noise. Means a small amount of noise if you introduce to the critical dam systems, they can either become the overdam systems or the underdam systems. The next point is when the system has gain margin 0 dB and the phase margin is 0 degree, then the system is said to be marginally stable system. This point I have already told you so many number of times. So listen carefully. Finally I am going to tell you For a characteristic equation ASQ plus BSQ plus CS plus D is equal to 0, for a system to be stable, AD is less than BC, then the phase of frequency is lesser than the phase cause of frequency, as well as both the gain margin and the phase margin, both are said to be positive. So gain margin in dB is positive, phase margin in degree is also positive. Similarly, when AD is equal to BC, we say it is a marginally stable system. It means that gain cause of frequency is equal to phase cause of frequency. So then gain margin is equal to 0 dB, as well as phase margin is also equal to 0 degree, or you can say both are equal. Whenever AD is greater than BC, we say it is a unstable system. So therefore, gain cause of frequency is greater than phase cause of frequency, and also we can say that both the gain margin in dB is negative, phase margin in degree is also negative. So this point always you have to keep in your mind. The next point is, if the loop gain function g of h of s is a stable function, then the closed loop system may or may not be stable. I have already told you, whenever the open loop transfer function, if it is a stable, then a closed loop transfer function can be either stable or unstable. This one I have already told you so many number of times. So let me write here. Suppose it's the open loop system and it's the closed loop system. So let me write here so that we can be able to remember this concept also. So this is the open loop system and this is the closed loop system. Sometimes, suppose if the open loop system is unstable, then the closed loop system can be either stable or it can be either unstable. Suppose if the open loop system is stable, then the closed loop system can be either stable or unstable. So these things always you have to keep in your mind. So therefore we can say that whenever the open loop system is unstable, then the closed loop system can be either stable or unstable. If the open loop system is stable, then the closed loop system can be either stable or unstable. So this point always you have to keep in your mind. So we can say, if the open loop gain g of h of s is a stable function, then the closed loop system can be open loop system may or may not be stable. So you can see clearly, whenever the open loop system is stable, it indicates that the closed loop system can be either stable or unstable. Similarly, if the open loop system is unstable, then the closed loop system can be either stable or unstable. So these things always you have to keep in your mind. The next point is, Bode plots the open loop magnitude and the phase angle responses for undamped sinusoidal inputs, which are plotted separately as a function of real frequency. So basically, we can say Bode plot. So in the case of Bode plot, we have two things: the magnitude as well as the phase angle. For the open loop transfer function, we are going to take the magnitude, and also the phase angle also we are going to plot. For the undamped sinusoidal input means the input is having the continuous oscillations. They are going to present for all time. For different types of frequency, real frequency, we are going to plot. For the polar plots the open loop response due to underdamped sinusoidal as a function of real frequency. Polar plot means I have already told it's the magnitude and the phase angle, both are going to combine to that. So it is going to plot the open loop response due to underdamped sinusoidal as a function of real frequency. There also the frequency is real, which is omega is equal to 0 to omega is equal to infinity. So we are going to take the real frequency, but there we are going to consider the underdamped sinusoid means the sinusoid is going to decay, or we can say the oscillations are going to vanish as time goes on. So whereas Nyquist plots the open loop response due to damped sinusoidal inputs as a function of complex frequency. So Nyquist plot plots the open loop response due to damped sinusoidal inputs as a function of complex frequency. I already told you in the case of Nyquist plot, we have four polar plots. In the case of, there is a S is equal to sigma plus j omega. Sometimes sigma is equal to 0, sometimes sigma is not equal to 0. So therefore we can say, finally, we are going to consider the complex frequency, because we have to report the real part as well as the imaginary part. So we are going to consider the complex frequency, but there also we are going to do the analysis for the open loop system only. So Nyquist plots the open loop response due to damped sinusoid means we can say that the oscillations are going to decay. The next point is, Nicholas chart plots the closed loop response due to sinusoidal inputs as a function of real frequency. So Nicholas chart plots the closed loop response due to sinusoidal inputs as a function of real frequency. So basically Nicholas chart is basically going to plot the closed loop response due to sinusoidal inputs as a function of real frequency. So this one always you have to keep in your mind, which is the Bode plot, the polar plot, and the Nicholas chart. These three plots are going to consider only the real frequency, whereas the Nyquist plot is going to consider the complex frequency. Next point is the Bode plot, the polar plot, and the Nyquist plot. They are going to do the analysis for the open loop system, whereas the Nicholas chart is going to do the analysis for the closed loop system. These point always you have to keep in your mind. So for a Bode plot, we are going to consider the undamped sinusoidal input. Whereas for the polar plot, we are going to consider the undamped sinusoidal input. Whereas for Nyquist plot, we are going to consider the damped sinusoidal input. Whereas for the Nicholas chart, we are going to consider the sinusoidal inputs or undamped sinusoidal inputs. So finally listen carefully. For the Bode plots, polar plots, and the Nicholas chart, these are going to use only the real frequency, whereas the Nyquist plot is going to use the complex frequency. In the case of Bode plot, it is going to use the undamped sinusoidal inputs, whereas the polar plot is going to use the undamped sinusoidal input, whereas the Nyquist plot is going to use the damped sinusoidal inputs, whereas the Nicholas chart is going to use the sinusoidal inputs. And also, we can say that the Bode plot, polar plot, and the Nyquist plot, they are going to do the analysis for the open loop systems, where the Nicholas chart is going to do the analysis for the closed loop system. So finally, I can say Bode plot, polar plot, and the Nicholas chart, they are going to use only for the real frequency, whereas the Nyquist plot is used, it is going to use the complex frequency. Whereas the Bode plot, polar plot, and the Nyquist plot, they do the analysis for the open loop system, whereas the Nicholas chart it can does the analysis for the closed loop system. And also, the Bode plot is going to include the undamped sinusoidal inputs. Polar plot is going to use the underdamped sinusoidal inputs, whereas the Nyquist plot is going to use the damped sinusoidal inputs, whereas the Nicholas chart is going to use the purely sinusoidal inputs. So these things always you have to keep in your mind. The next point is, from G of H of S, we draw the root locus, as well as Bode plot, as well as the Nyquist plot. I already told you, from the open loop transfer function G of H of S only, we are going to draw the root locus, as well as the Bode plot, as well as the Nyquist plot. Or you can say even the polar plot also we are going to draw from this one only. So it can be only polar plot. So even we can say polar plot also, because a combination of polar plot is nothing but Nyquist plot. So let me write here polar plot also. So therefore we can say from the open loop transfer function G of H of S only, we are drawing the root locus, as well as the Bode plot, as well as the Nyquist plot, as well as the polar plot. So this point always you have to keep in your mind. So from the open loop transfer function G of H of S only, we are drawing the root locus, as well as the Bode plot, as well as the Nyquist plot, as well as the polar plot. So this point always you have to keep in your mind. So therefore we can say from the open loop transfer function G of H of S only, we are drawing the polar plot, Nyquist plot, Bode plot, and the root locus. So this point always you have to keep in your mind. So from the open loop transfer function G of H of S, we are drawing the root locus, Bode plot, Nyquist plot, and the polar plot. So this point always you have to keep in your mind. So I can say finally, from the open loop transfer function only, we are drawing the root locus, we are drawing the Bode plot, we are drawing the Nyquist plot, as well as the polar plot. The next point is, from open loop transfer function G of S, H of S, we are drawing the polar plot. And if it is not going to enclose the minus 1 plus J0, then the open loop transfer function G of H of S is said to be stable. It means that no pole of the open loop transfer function G of H of S is going to lie in the arches of the S plane. So this point I have already told you. So from the open loop transfer function G of H of S, we are basically drawing the polar plot. And if this polar plot is not going to enclose the minus 1 plus J0, then default we can say that the open loop transfer function G of H of S, it is said to be stable, and it indicates that no pole of the G of H of S is going to lie in the origins of the S plane. See, whether it is an open loop system or whether it is a closed loop system, if the poles are not going to lie on the arch of S plane, we can say stable. It is the same concept applied for both the open loop system as well as the closed loop system. So therefore we can say that finally, from the open loop transfer function G of H of S, we are going to draw the polar plot. And if this polar plot is not going to enclose the minus 1 plus J0, then the open loop transfer function is said to be stable. It indicates that no pole of the G of H of S is going to lie in the RHS of S plane. Suppose if this polar plot is not going, suppose if this polar plot is going to cross the mass of like J0 means we say it is a mass unstable system. Suppose if this polar plot is going to influence the mass of like J0 means we can say it is said to be unstable system. Say what I told you, suppose if you are eating too much, your body will become unstable. Same thing, if it is going to influence the mass of the J0 means it will become unstable. So this part always you have to keep in your mind. So therefore finally I can say from the upper transfer function G of H of S, we are going to draw the polar plot. And if this polar plot is not going to influence the mass of like J0, then definitely we can say the open transfer function G of H of S is said to be stable. It indicates that no pole of the G of H of S is going to lie in the arches of the S plane. And also one more important point here is, suppose if this polar plot is going to cross the mass of like J0, it indicates that the open transfer function is said to be mass unstable system. If this polar plot is going to enclose the mass of like J0 means the system is said to be unstable system. Enclosing means basically I ordered through the shortcut, which are eating more and more, will become unstable. Similarly, if the polar plot is going to enclose the point means it is said to be unstable. This point always you have to keep in your mind. The next point is, higher the resonant peak, higher is the maximum overshoot of the step response. So higher the resonant peak is nothing but the resonant peak is MR. I've already told you its formula is equal to 1 by 2 zeta under root over 1 minus zeta square. Then what is the MP? MP is nothing but e to the power of minus zeta pi by under root over 1 minus zeta square. So this resonant peak is basically belongs to frequency domain specification, whereas this MP is belongs to time domain specification. This one I've already told you so many number of times. So this resonant peak is basically belongs to the frequency domain specification, whereas this MP is belongs to the time domain specification. And I've already told you one important point, which is whenever the zeta is lesser than 0.707, then the resonant peak is exist, or we can say it is exist. It is going to be exist. So therefore, the P40 is also going to be exist. It is going to be exist. Whereas zeta is greater than 0.07. Then what we can say? Simply we can say that if zeta is equal to, or we can say zeta is equal to, then MR is equal to 1. MR is equal to 1. So here it is greater than 1. It is greater than 1. Or simply we can say exist of greater than 1. Then MP is also going to get exist. But if zeta is greater than 0.707, then the resonant peak is not exist. Whereas the MP is going to be exist. So this one always you have to keep in your mind. So therefore we can say, whenever the zeta value is less than 0.707, the resonant peak value is greater than 1. Whereas the peak which value is always going to get exist. Whenever zeta is equal to 0.707, the resonant peak value is equal to 1. Whereas the peak value is equal to exist. Whereas it is greater than 0.707, the resonant peak won't even exist, whereas the peak is going to be exist. So we can say for some range of zeta, MR is not going to get exist, but MP is going to get exist. So what is the meaning of this one? If MR exists, then MP exists. If MP exists, then MR may or may not exist. So we can say if MR exists means compulsory MP is going to get exist. But if MP is existing means it is not compulsory that MR will exist. So this part always you have to keep in your mind. So whenever the MR increases, then MP is also going to get increases. So this one I am trying to tell you. So whenever MR increases, then MP is also going to get increases. MR is the specification in the frequency domain and MP is the specification in the time domain. As MR increases, MP is also going to get increases. So higher the resonant peak, higher is the maximum overshoot of the step response. So higher the resonant peak, higher is the maximum overshoot of the step response. This one always you have to keep in your mind. So these things always you have to keep in your mind. So now the next point is for parallel resonant circuit. For parallel resonant circuit, the formula you have to remember, which is omega d is equal to under over omega n square minus tan it by 2 whole square. Whereas omega d is called as the damped frequency, omega n is called as the resonant frequency, and BW is called as the damping. So this formula always you have to keep in your mind. So for a parallel resonance circuit, omega d is equal to under root over omega n square minus bandwidth by 2 whole square. For omega d is called as the damped frequency, omega n is called as the resonant frequency or natural frequency also you can call. Whereas BW is called as the bandwidth. So this formula always you have to keep in your mind. So finally I can say for a parallel resonance circuit, omega d is equal to under root over omega n square minus bandwidth by 2 whole square. Omega d is called as the damped frequency and omega n is called as the resonant frequency or natural frequency and BW is called as the bandwidth. So these formulas always you have to keep in your mind. So finally I can say for parallel resonance circuit, omega d is equal to under root over omega n square minus bandwidth by 2 whole square. Omega d is called as the damped frequency, omega n is called as the resonant frequency or natural frequency and BW is called as the bandwidth. So these points always you have to keep in your mind. So finally, I can say for a parallel resonance circuit, I can say that omega d is equal to under root over omega n square minus bandwidth by 2 whole square. Whereas omega d is called as a damped frequency, omega n is called as a resonant frequency, or it is also called as a natural frequency. It is called as a natural frequency. So this one always you have to keep in your mind. So this is called as a natural frequency. Whereas BW is called as a bandwidth. All its units are radians per second or radians also we can call. So finally I can say for a parallel resonance circuit, omega d is equal to under root over omega n square minus bandwidth by 2 whole square. Omega d is called as a damped frequency. Omega n is called as resonant frequency or natural frequency. Whereas BW is called as the bandwidth. The next point is the polar plot of open loop transfer function g of h of s does not touches the negative real axis, then we can say gain margin is said to be infinity. It means that the closed loop poles always they are going to lie in the edge of S plane for all range of the gain. So whenever the polar plot of the open loop transfer function it is not going to cut the negative real axis, it indicates that the gain margin is said to be infinity. So therefore, the closed loop transfer function, it means that the closed loop poles always going to lie in the edge of S plane for all the range of k. It indicates that the system is stable for all the range of k. So listen carefully. If whenever we are going to draw the polar plot of the g of h of s, and if it does not going to touch the negative real axis, it indicates that the gain margin is said to be infinity. It indicates that the closed loop poles are going to lie in the edge of S plane for all the range of k. So therefore the system is said to be stable. So finally, I can say that whenever you are going to draw the polar plot of the open loop transfer function, and if this polar plot is not going to touch the negative real axis, then we can say the gain margin is said to be infinity. It indicates that all the closed loop poles are going to lie in the edges of S plane for all the range of k. So that's we can say the system is said to be stable. So finally, I can say that whenever you are going to draw the polar plot of the open loop transfer function g of h of s, then if it is not going to touch the negative real axis, it indicates that the gain margin is equal to infinity. It indicates that all the closed loop poles are going to stay in the LHS of the S plane for all the range of k. So therefore, we can say the system is said to be stable. So finally, I can say whenever you are going to draw the polar plot of the open loop transfer function g of h of s, and if it is not going to touch the negative real axis, then we can say the gain margin is said to be infinity. It indicates that the closed loop poles are going to lie in the edge of S plane for all the range of k, which is from 0 to infinity. So we can say for all the range of k, the system is said to be stable. So these points always you have to keep in your mind. The next point is, see, suppose f square is equal to a, then what is the meaning of s? S is equal to plus or minus under root over a. This is the general way. Suppose if s square is equal to minus a, then s is equal to under root over minus a, which is equal to plus or minus j into 2k. So listen carefully. If s square is equal to a, means s is equal to plus or minus under root over a. If s square is equal to minus a, means s is equal to plus or minus j into under root over a, because j is equal to under root over minus 1. So this one we can say here j is equal to under root over minus 1. So whenever s square is equal to a, means s is equal to plus or minus under root over a. If s square is equal to minus a, means s is equal to plus or minus j into under root over a. So this is a very simple thing. I don't need to explain more and more about this one. So these points always you have to keep in that mind. Now we'll discuss some more important points here, which is some true facts. Some true facts, some true statements we are going to discuss. So let's see the statements. The polar plot has limitations for portraying the frequency response of the system because the calculation of the frequency response is tedious and does not indicate the effect of the individual poles as well as the zeros. The polar plot has limitations for portraying the frequency response of the system because the calculation of the frequency response is very tedious and does not going to indicate the effect of the individual poles as well as zeros. So I already told you, in the case of polar plot, we are going to consider the log of the Euclid transfer function as well as the phase angle of the Euclid transfer function. By varying the frequency omega from 0 to infinity, we are going to plot the locus that is called as a polar plot. So polar plot has basically, it has some limitations for portraying the frequency response of the system because the calculation of the frequency response is very tedious and it does not going to indicate the effect of the individual poles as well as zeros. So for each and every frequency, what is the magnitude and what is the frequency, what is the phase angle? These two things we have to figure out. So definitely it is a very severe pain in the neck and also it is not going to indicate what is the individual effect of the poles and zeros. It is going to tell you the overall magnitude, overall phase angle, but it can never tell you the individual effect of the poles as well as the zeros. So finally I can say the polar plot has some limitations for portraying the frequency response of the system because the calculation of the frequency response is very tedious and also it is not going to indicate the effect of the individual poles as well as zeros. So finally I can say simple switches. See in the case of polar plot, we are going to take the length of the Euclid transfer function as well as the phase angle of the Euclid transfer function. By varying the omega from 0 to infinity, we are going to consider the magnitude as well as the phase angle. These two things we are going to plot in the explain. That is called as a polar plot. See, calculating the magnitude phase angle for each and every value of omega is a very severe pain in the neck and also it is going to tell you the overall effect of the magnitude as well as the phase angle by considering all the poles and zeros. But it will never tell you the individual effect of the poles and zeros in the case of polar plot. The next point is the cutoff rate indicates the ability of the system to distinguish the signal from the noise. The cutoff rate is going to indicate the ability of the system to indicate the signal from noise. So basically with the help of cutoff rate, we are going to distinguish which is the noise and which is the actual signal. So in the case of low pass filter, any frequency below the cutoff frequency is a signal and any frequency below cutoff frequency is a noise. Similarly for the high pass filter, any signal with a frequency lesser than cutoff frequency is the noise and any signal above the cutoff frequency is said to be signal. So basically we are going to keep the cutoff in order to distinguish which is the signal and which is the noise. So the cutoff rate is going to indicate the ability of the system to distinguish the signal from the noise. So therefore we can say the cutoff rate is basically going to indicate the ability of the system to distinguish the signal from the noise. So with the help of cutoff rate, we are going to distinguish which is the signal and which is the noise. The next point is resonant frequency is the indicator of the speed of the transient response. Resonant frequency is the indicator of the speed of the transient response. Resonant frequency is the indicator of the speed of the transient response. So resonant frequency is, I have already told you, which is omega r is equal to omega n into root over 1 minus 2 zeta square. So this is called as a resonant frequency. So resonant frequency is the indicator of the speed of the transient response. So this point always you have to keep in your mind, which is the resonant frequency is the indicator of the speed of the transient response. So we can say the resonant frequency is basically it is the indicator of the speed of the transient response. So this resonant frequency is going to tell you that it is going to tell you the speed of the transient response. So we can say the resonant frequency is the indicator of the speed of the transient response. So basically this resonant frequency is going to tell you whether what is the speed of the transient response, whether it is a fast or whether it is a slow. This we can tell with the help of this resonant frequency. So resonant frequency is basically the indicator of the speed of the transient response. The next point is gain margin is the factor by which the gain of the system should be increased in order to drive it into the verge of the instability. So gain margin is the factor by which the gain of the system should be increased in order to drive it into the verge of the instability. I've already told you gain margin means That is the factor by which you have to increase the gain in order to make the system to become unstable. Suppose the gain margin is, suppose let me assume this is a some amount of gain margin is there. So here, this much amount of gain margin you have to increase for the system in order to make the system to go from stable to unstable region. So this point always you have to keep in your mind. So this much amount of gain margin you have to increase in order to make the system to become from stable to unstable region. So this point always you have to keep in your mind. So therefore we can say gain margin is a factor by which the gain of the system should be increased in order to drive it into the verge of the instability. So basically if you want to convert, so by this much amount of factor, you have to increase the gain in order to convert the system from stable to unstable. So therefore we can say gain margin is the factor by which the gain of the system should be increased in order to drive it into the verge of the instability. So gain margin is the factor by which the gain of the system should be increased in order to drive it into the verge of the instability. So finally I can say gain margin means this much amount of gain margin you have to increase for the system to become unstable. So finally I can say gain margin is a factor by which the gain of the system should be increased in order to drive it into the verge of the instability or unstable. The next point is Nicholas chart is used to determine the closed loop frequency response. I already told you Nicholas chart is basically it is used to determine the closed loop frequency response. So with the help of Nicholas chart we are going to figure out the closed loop frequency response. So Nicholas chart is basically used to determine the closed loop frequency response. So for the closed loop transfer function, what is the nature of the frequency response that we are going to figure out with the help of this Nicholas chart? And in the Nicholas chart doesn't have any 0 dB line. So Nicholas chart is not going to include any 0 dB. We have to have 0 dB line. It will never present in the case of Nicholas chart. So we can say with the help of Nicholas chart we are going to draw the closed loop frequency response as well as there is nothing like 0 dB line or 0 dB loop in the case of Nicholas chart. So this will always you have to keep in your mind. So we can say Nicholas chart basically Nicholas chart is basically used to determine the closed loop frequency response. And there is nothing like 0 dB loop or 0 dB line is not going to present in the Nicholas chart. So finally I can say Nicholas chart is basically it is used to determine the closed loop frequency response. And there is nothing like 0 dB line or 0 dB loop in the case of closed loop system. So finally I can say Nicholas chart is basically it is used to determine the closed loop frequency response. And there is nothing like 0 dB line or 0 dB loop in the case of Nicholas chart. So finally I can say Nicholas chart is basically it is used to determine the closed loop frequency response. And there is nothing like 0 dB line or 0 dB loop in the case of Nicholas chart. The next point is h of t is equal to d by dt of s of t. I have already told you this one so many number of times, but finally let me tell you here. I have already told you unit step signal is the integration of the impulse signal. So similarly, u of t response is the s of t and delta of t response is the h of t. So same thing, we are also going to follow the same relation. So you can see clearly u of t is equal to integration of as into t delta of t dt. So u of t response is h of t, delta of t response is h of t. So u of t response is s of t, delta of t response is h of t. So we are also going to follow the same relation. So step response is the integration of the impulse response. Similarly, delta of t is a derivative of the step signal. Similarly, the response is also going to follow the same relation. Delta of t response is h of t and d by dt of u of t response is s of t. So therefore we can say the response is also going to follow the same relation. So therefore we can say h of t is equal to d by dt of s of t. H of t is follows the impulse response and s of t is follows the step response. So listen carefully. For the impulse response, whenever the limit tends to infinity, h of t should be equal to 0, then only we can say this is a stable system. So I have already told you for the impulse response, when t tends to infinity, the impulse response tends to 0, then only we can say this is a stable system. Listen carefully. Whenever we listen carefully, as time tends to infinity, if the impulse response is tending to 0, then we can say this is a stable system. But as a t tends to infinity, the impulse response is going to reach a finite value, then it is called as a marginally stable system. But as t tends to infinity, if the impulse response is also increases, then we can say it is said to be unstable system. So listen carefully. Finally, I can say As t tends to infinity, if the impulse response is going to equal 0, it is called as a stable system. As t tends to infinity, if the impulse response is going to infinite value, it is called as the marginal stable system. But as t tends to infinity, if the impulse response is goes on increases, then we can say it is said to be unstable system. So finally, I can say as t tends to infinity, the impulse response is going close to 0, it is called as a stable system. But as t tends to infinity, if the impulse response is going to infinite value, it is called as a marginal stable system. But as t tends to infinity, if the impulse response is having an increasing value, we can say this is an unstable system. The next point is always try to keep the open transfer function g of h of s in a time constant form for the Bode plot as well as the Nyquist plot. So I already even for the root locus also same thing. In the root locus also try to keep it in the this one also. So root locus also same thing. Root locus also same thing. So always try to keep the open transfer function g of s in a time constant form for the Bode plot, Nyquist plot as well as the root locus plot. So this one always you have to keep in your mind. So therefore we can say always try to keep the open transfer function g of h of s in the case of time constant format for the Bode plot analysis, Nyquist plot analysis as well as the root locus analysis also. This point always you have to keep in your mind. So finally I can say always try to keep the open transfer function g of h of s so always try to keep the open transfer function g of h of s in the time constant format for doing the analysis of the Bode plot, Nyquist plot as well as the root locus analysis. So finally I can say always try to keep the open transfer function g of h of s in the time constant format for doing the analysis of the Bode plot, Nyquist plot and root locus. The next point is only lead compensator is going to input the transient response, but not the lag compensator and PI controller. See, I have already told this point so many number of times. Lead compensator is used to improve only the transient response and it is going to degrade the steady state response. Similarly, the lag compensator is used to improve only the steady state response and it is going to degrade the transient response. Lead compensator means PD controller, lag compensator means PI controller. This one I have already told you so many number of times. So finally, I can say lead compensator is used to improve the transient response, but it is going to degrade the steady state response. Whereas the lag compensator is used to improve only the steady state response, so it is going to degrade the transient response. So the lead compensator means PD controller, lag compensator means PI controller. This point I already told you so many number of times. Now we are going to discuss the another point. The point is a phase shift compensator is going to improve both the gain crossover frequency as well as the bandwidth. It indicates that the gain crossover frequency increases as well as the bandwidth is also going to get increases. This point I have already told you so many number of times, which is in the case of phase shift compensator, it is going to improve only the transient response of the system. So therefore it is going to degrade the steady state response of the system. So because of this, what is going to happen? As part of the response will increase, indicates that rise time is going to get decreases. As the rise time decreases, the bandwidth will increase because the product is always equal to constant. And also, the damping ratio is also going to get increases because of this one. As the damping ratio increases, the P equals is going to get decreases. The P equals is going to get decreases. This point always you have to keep in mind. See, as the rise time decreases, what we can say, then once the rise time is going to decrease, we can say the damping ratio is going to get increases. So P equals is going to get decreases. So both are always inversely proportional, damping ratio and the P portion. And also the gain crossover frequency is also going to get increases. And one more thing is, this is nothing but it is a PD controller. The PD controller. So these things I have already told you so many number of times. The next point is, in the transfer function of the compensator, remove the common terms and then decide whether it is a phase shift compensator or the phase lag compensator. Suppose they are given some transfer function and they are asking what is the type of this compensator, then you have to factorize numerator and denominator and remove the common terms, and then removing the new transfer function that we are going to get. So based on this, we have to check whether it is a phase shift compensator or the phase lag compensator. So finally I can say, suppose in the question they are given some transfer function and they are asking what type of compensator it is, means first you have to cancel out the common terms And based on that, we have to now first remove the common terms, and then based on this new transfer function, try to figure out what type of compensator it is. If the zero is closer to origin when compared to pole, it is called as a phase-side compensator. If the pole is closer to origin when compared to zero, it is called as a phase lag compensator. So this point I already told you so many number of times. So therefore we can say in the question they are given some transfer function, then we have to remove the common terms, then decide what type of compensator it is. So there is a phase lag compensator or phase lag compensator. The next point is in the Bode plot, the last line has a slope which is equal to. So basically here in this point they are asking that suppose in the Bode plot the last line or the last asymptotic line, what is the slope of this one? What is the slope of this one means I already told you. So in the open transfer function we have suppose p number of poles and z number of zeros. So p is follows the number of poles of g of h of s, and this is for the number of zeros of g of h of s. Or simply we can say p indicates number of open loop poles of the open loop transfer function, or this indicates the number of zeros of the open loop transfer function. You can call it anything. The formula is p into each pole is going to contribute -2 decimals per decade plus, and z indicates number of zeros. So each zero is going to contribute +2 decimals per decade. So if you solve this one, we are going to get this one. Similarly, suppose in the Bode plot, if you want to find what is the last line as the phase angle of, so similarly p into each pole is going to contribute -90 degrees plus z into each zero is going to contribute +90 degree. Each zero is going to contribute +90 degree, and each pole is going to contribute -90 degree. Is substitute simplify, then you are going to get the in the Bode plot with the last asymptotic line will have this much amount of phase angle. So this is also easy to remember. So therefore, if you listen carefully, in the case of Bode plot analysis, the last line has a slope which is equal to p into -2 decimals per decade plus z into +2 decimals per decade. And p indicates the number of poles of the open loop transfer function g of h of s, and it indicates the number of zeros of the open loop transfer function g of h of s. Similarly, the same manner in the Bode plot, if you want to figure out the last line, how much amount of phase angle it will contribute, means we can say that p into -90 degrees plus z into +90 degrees. So this point always you have to keep in your mind. The next point is the time constant form for the Bode plot. So I already told you, always you have to keep the open loop transfer function always in the case of the time constant format for doing the analysis. This h of is equal to k into s to the power of n into 1 plus st1 into 1 plus st2 into 1 plus st3 by s to the power of n into 1 plus s into t4 into 1 plus s into t5 into 1 plus s into t6, then s square by omega n square plus 2 zeta s by omega n plus 1. So this is the standard way of writing. So if you see clearly, always we have to write the open loop transfer function g of h in the time constant format for doing the analysis, either for the Bode plot or either for the replot or either for the Nyquist plot. Then what is the cutoff frequency? Here the cutoff frequency is equal to 1 by t1, here the cutoff frequency is equal to 1 by t2, here the cutoff frequency is equal to 1 by t3, here the cutoff frequency is equal to 1 by t4, here the cutoff frequency is 1 by t5, here the cutoff frequency is 1 by t6, here the cutoff frequency is omega n. So this one I have already told you. So each and every term try to figure out the corresponding cutoff frequencies. So each zero is going to contribute a +2 decimals per decade, and each pole is going to contribute a slope of -2 decimals per decade. And this one, this is nothing but a pole. So quadratic pole is going to contribute a -4 decimals per decade, and the quadratic zero is going to contribute a +4 decimals per decade. So this one I already told so many number of times. So always try to keep in the format of the time constant format for doing the analysis. The next part is introduction of the integral action in the fall path of a multi-feedback system results in a system with the no steady state error. So whenever we are going to introduce a integral action in the case of fall path transfer function with a unit gain, then what is going to happen? Basically, you are adding zeros. Suppose let me take here g of h of s. G of h of s something here, some transfer function, something here. So now we are adding it, it will become 1 by s here. So 1 by s we are going to get. So indicate that we are going to increase the order of the system by 1 unit, as well as we are going to increase the power of the system by 1 unit, as you can see clearly from this expression. And also As the number of nodes increases, the root node is going to shift the direction of display. So stability is also going to get decreases. See, adding nodes means we can say this is a lag compensator. Lag compensator means PI controller. So therefore, it is going to improve only the steady state error, but it is going to degrade the transient response. So improving the steady state response means it is going to decrease the steady state error. Means there will be no steady state error. Means steady state error will be zero, absolutely zero in that case. So this will always you have to keep in the mind. So therefore we can say finally, whenever you are going to introduce the integral or we can say integrator in the case of all part of a transfer function, then basically we are going to increase the parallel system by 1 unit as well as we are going to increase the parallel system by 1 unit. So whenever we are going to add the poles, the root method is going to shift to the house of first plane, so therefore the system will become unstable. Say adding poles is something like PI controller or simply we can say the lag compensator. So because of this, it is going to improve only the steady state response, but not it is going to degrade the transient response. So because of this, improving the steady state response, the steady state error will decrease. So finally, it will become steady state error is equal to 0. So there will be no steady state error. The next point is phase clear compensator is going to increases the bandwidth and hence decreases the rise time. As it is going to improve the damping, so overshoot also decreases. So this point I already told you in the case of the phase clear compensator. Phase clear compensator means it is going to improve only the transient response of the system. So it is going to degrade the steady state response also. So now because of this, the zero is closer to origin when compared to pole in the case of phase clear compensator. So how it is going to improve the transient response. So definitely the rise time is going to get decreases. So as the rise time decreases, definitely the bandwidth will increase because the clock is always equal to constant. So therefore now the damping ratio is always going to get increases in the case of the PD controller. So as the damping ratio increases, then what is going to happen? The peak quotient is going to get decreases because both are always inversely proportional. So both are always inversely proportional. And also here, and the peak quotient, so peak quotient is also going to get decreases. So because both are always inversely proportional. So therefore this point always you have to keep in mind. So whereas the gain crossover frequency is also going to get increases. The gain crossover frequency is also going to get increases in this one. So this point always you have to keep in mind. Whereas the steady state error is going to get increases. This point always you have to keep in mind because it is going to improve only the transient response, but not the this is going to be the steady state response. So because of this, the size error is going to get increases. So finally I can say phase clear compensator means we can say it is going to improve only the transient response of the system and is going to be the steady state characteristics of the system. So as it is going to improve the transient response, so then the rest time is going to get decreases. So bandwidth is going to get decreases because the problem is always equal to constant. So in this case, it is going to improve damping of the system. So therefore, the peak quotient is going to get decreases because both are always inversely proportional to each other. It is also going to improve the gain crossover frequency of the system as it is going to degrade the steady state response. So therefore, the size error is going to get increases. And also, PD means we can say we are adding zeros. So because of this, the type and the order of the system will never be increases. It will remain as it is the previous case. And also, the stability is going to get increases because we are adding zeros. So therefore, the stability is going to get improved. But there is a differentiator. PD means differentiator is there. So because of this, the noise is going to get increases. So signal to noise ratio is going to get decreases. So this point always you have to keep in your mind. The next point is the determinant of Zi minus A is equal to 0. It is called as the characteristic equation in the case of discrete time system. As I've already told you, if you want to find what is the characteristic equation in the case of the continuous time system, it is the determinant of Si minus A is equal to 0. So these 2 points always you have to keep in your mind. So the determinant of Zi minus A is equal to 0 is a characteristic equation in the case of discrete time system, and determinant of Si minus A is equal to 0 is a characteristic equation in the case of continuous time system. So these 2 points always you have to keep in your mind, which is the determinant of Zi minus A is equal to 0 is the characteristic equation in the case of the discrete time system, whereas the determinant of the Si minus A is equal to 0 is called as the characteristic equation in the case of the continuous time system. These 2 points always you have to keep in your mind. I can say clearly finally the determinant of Zi minus A is equal to 0 is called as the characteristic equation in the case of the discrete time system, whereas the determinant of the Si minus A is equal to 0 is called the characteristic equation in the case of the continuous time system. The next point is a transfer function of a control system does not have pole zero cancellation, then compulsory the system is controllable as well as observable. Suppose in the case of transfer function, if there is nothing like pole zero cancellation, then definitely we can say the system is said to be controllable as well as observable. So this is the default point always you have to keep in mind. So therefore you can say if you take a transfer function of a control system and if it is not having any pole zero cancellation, there are no common terms, then we can say that system is said to be both controllable as well as observable. So finally, I can say, suppose if you take a transfer function and if there is no pole zero cancellation, there is no common terms in the numerator denominator, then that is called as a compulsory. The system is said to be controllable as well as observable. The next point is the characteristics of the non-linear system. So now we are going to discuss some characteristics of the non-linear systems. So now we are going to discuss some characteristics of the non-linear systems. If the input is a sine wave of radial frequency omega, then the output is general is non-sinusoidal containing frequencies which are multiple of omega. Suppose if the input is a sine wave of radial frequency omega, then the output is generally is non-sinusoidal containing frequencies which are multiple of omega. I have already told you, suppose if we take a non-linear system and we are giving a signal having the frequency omega, then the output will have multiple frequencies like omega, 2 omega, 3 omega, and so on. The next point is the jump response may occur. So basically, in the case of non-linear system, the output may have the jump response, sudden change of output. You can get in the case of non-linear systems. The next point is the system exhibits the self-sustained oscillations of fixed frequency as well as amplitude. The system is going to exhibit the self-sustained oscillations of fixed frequency as well as the amplitude. The next point is the response to a particular test signal may not be tied to the behavior to the other inputs. I have already told you, in the case of LTI systems, if you give delta of t, you are going to get h of t, then output may not be always equal to x of t combination of h of t because it is a valid only for LTI systems but not for non-LTI systems. So I have already told you the difference between a linear system as well as a non-linear system. In the case of linear systems, if you give the input signal as frequency omega, then the output signal is also having the same frequency omega only. Only there is a change in the magnitude as well as a phase angle, but the frequency will be same in the case of input as well as output in the case of linear systems. For linear systems, but whereas for the non-linear systems, if the input has a signal of frequency omega, then output will have a frequency which is omega, 2 omega, and 3 omega, and so on. In the case of LTI systems, in the case of linear systems, always the output will be always continuous in nature. There will be no sudden jumps. Whereas in the case of non-linear systems, there is a sudden response. The jump response may occur in a sudden amount of response you are going to see. Sudden change in output you can see. And in the case of non-linear systems, the system is going to exhibit the self-sustained oscillations of fixed frequency as well as amplitude. So, even though input is equal to 0, output is not equal to 0, which is having some fixed frequency of oscillations as well with some amplitude. Even though input is equal to 0, but still, output is not equal to 0 in the case of non-linear systems. It will have some self-sustained oscillations of fixed frequency as well as amplitude we can see in the case of non-linear systems. In the case of linear systems, I have already told you, suppose if you are going to give the signal delta of t, you are going to give h of t. So with the help of h of t, you can figure out the output for any type of input, but this is not the case in the case of non-linear systems. So these points always you have to keep in your mind. So finally I can say the characteristics of the non-linear systems, which are if the input is a sine wave of radial frequency omega, then the output in general is a non-sinusoidal containing frequencies which are multiple of omega. Jump response may also even occur. The system is going to exhibit the self-sustained oscillations of fixed frequency as well as amplitude, and the response to a particular test signal may not be guided to the behavior to the other inputs. The next point is, if any one of the state variable is independent of the control signal u of t, the whole process is said to be completely uncontrollable, and there is no way of driving this particular state variable to a desired state in a finite amount of time by means of a control effort. See, I have already told you what is the basic agenda of controllable. The system is said to be controllable if all the state variables are controlled. Similarly, a system is said to be observable if all the state variables are measurable. So this point always you have to keep in your mind. So if all the state variables are controlled, then it is called the whole system is said to be controllable. If all the state variables are measured, then we consider the overall system is said to be measurable. observable. So therefore, even if any state variable is uncontrolled, then the whole system is said to be uncontrollable. If any mass variable is unmeasurable, then the overall system is said to be unobservable. So this one I have already told it so many number of times. So if any one of the state variable is independent of the control signal u of t, the whole process is said to be completely uncontrollable, and then there is no way of driving this particular state variable to a desired state in final time by use of a control effort. See, controllable means all the state variables should be under the control of the input signal. If anyone is not under the control of the input signal, then we can say the whole process is said to be uncontrollable. So listen carefully. If all the state variables are under the control of the input, then we can say it is a controllable system. If any one of the state variable, if it is not under the control of the input signal, then we can say the overall system is said to be uncontrollable. So if any one of the state variable is independent of the control signal u of t, the whole process is said to be completely uncontrollable, and there is no way of driving this particular state variable to a desired state in a finite amount of time by means of a control effort. So finally I can say, if any one of the state variable is independent of the control signal u of t, the whole process is said to be completely uncontrollable, and there is no way of driving this particular state variable to a desired state in a finite amount of time by means of a control effort. So finally I can say, if any one of the state variable is independent of the control signal u of t, the whole process is said to be completely uncontrollable, and there is no way of driving this particular state variable to a desired state in the finite amount of time by means of a control effort. So finally, I can say in simple words, see, if all the state variables are under the control of the input signal, then we can say it is said to be controllable. Even if any one of the state variable is not under control of the input signal, then it is said to be uncontrollable system. So this point always you have to keep in your mind. The next point is the methods to analyze the non-linear systems of. So now we are going to discuss the different type of methods in order to analyze the non-linear systems, which are phase plane method, discarding function method, and the piecewise function method. So these are the three methods in order to analyze the non-linear systems, which are the phase plane method, describing function method, as well as the piecewise function method. Whereas the methods to analyze the LTI systems are the Lipnos method. So this point always you have to keep in your mind. So the methods to analyze the nonlinear systems are the phase plane method, describing function method, and the piecewise function method. Whereas the methods to analyze the LTI systems are the Lipnos method. So this point always you have to keep in your mind. So therefore we can say the methods to analyze the non-linear systems are the phase plane method, describing function method, and the piecewise function method. Whereas the methods to analyze the LTI systems are the Lipnos method. So finally, I can say the methods to analyze the non-linear systems are the phase plane method, describing function method, and the piecewise function method. Whereas the methods to analyze the LTI systems are the Lipnos method. So finally, I can say the methods to analyze the non-linear systems are the phase plane method, describing function method, and the piecewise function method. Whereas the methods to analyze the LTI systems are the Lipnos method. The next point is the discrete time systems are more accurate as well as more stable when compared to continuous time system. This point I already told you several number of times, which is the discrete time systems are said to be more accurate as well as more stable when compared to the continuous time system because they can withstand a huge amount of noise. They are very less sensitive to noise also, whereas the continuous time systems are very highly sensitive to noise. So we can say the discrete time systems are more accurate and more stable, and they are less sensitive to noise also. So we can say the discrete time systems are more accurate and more stable, and they are very less sensitive to noise when compared to continuous time system. So finally, I can say the discrete time systems are more accurate and more stable, and they are less sensitive when compared to the continuous time system. The next point is, see, basically we are going to apply the initial value theorem and the final value theorem for both the continuous time system as well as the discrete time system. See, in the case of continuous time system, what is the initial value theorem? F of 0 is equal to limit s tends to infinity s into f of s. Whereas the final value theorem in the case of continuous time system is equal to limit s tends to 0 s into f of s. Same thing here also we are going to apply. In the case of discrete time system, the initial value theorem is f of 0 is equal to limit z tends to infinity, here it will be 1 minus z inverse into f of z. So, like this you have to write. In place of that, if you substitute infinity, then what you are going to get combined is something like 0. So, 1 minus 0 into f of x second, 1 into f of this one, f of the same thing you are going to get. Similarly, the final value theorem in the case of this time system is f of infinity is going to limit z tends to 1, 1 minus z to the power of minus 1 into f of z. So, if you see clearly here, s into f of s here, 1 minus z to the power of minus 1 into f of z. So, this is the only thing which is common. Here s is equal to infinity means z is equal to infinity. Here s is equal to 0 means z tends to 1. So, this is the only difference that you have to keep in your mind. So, listen carefully. Here the continuous time case it is here s into f of s here, 1 minus z to the power of minus 1 into f of z. Here s tends to infinity means z tends to infinity. Here s tends to 0 means z tends to 1. So, this is the only thing that you have to keep in your mind. So, this is the thing you have to keep in your mind, which is if you are going to compare the continuous time system as well as discrete time system, here s into f of s means here 1 minus z to the power of minus 1 into f of z. Here s tends to infinity means z tends to infinity. S tends to 0 means z tends to 1. So, this point always you have to keep in your mind. So, finally, I can say whenever you are going to compare both the continuous time system as well as discrete time system, here s into f of s is replaced by 1 minus z to the power of minus 1 into f of z, and s tends to infinity means z tends to infinity, s tends to 0 means z tends to 1. So, this is the only thing that you have to keep in your mind, and the remaining everything is same. The next point is the state transition matrix that represents the free response of the system, and also it is going to satisfy the homogeneous state equation. See, I have already told you, whenever the input is equal to 0, and you are going to get the output based on the initial condition, that is called as a free response. The free response is basically a representative with the help of the state transition matrix. So, what is a state transition matrix? Which is equal to the power of ut is called as a state transition matrix, which is Laplace inverse of the SA minus A. This is called as a state transition matrix. Laplace inverse of SA minus A. Laplace inverse of SA minus A whole inverse. SA minus A whole inverse. So, this is called as the Laplace inverse of SA minus A whole inverse. This is called as the state transition matrix. So, let me write it here. So, small correction here. So, listen carefully. Let me write it here. So, Laplace inverse of SA minus A whole inverse. So, this is called as the state transition matrix. So, the free response is basically represented with the help of the state transition matrix. Free response means we can say simply whenever the input is equal to 0, but still you are going to get the output because of the initial condition, that is called as a free response. And the state transition matrix is going to satisfy the homogeneous state equation. So, finally, I can say the state transition matrix is going to represent the free response of the system, and also it is going to satisfy the homogeneous state equation. So, finally, I can say the state transition matrix is going to represent the free response of the system, and also it is going to satisfy the homogeneous state equation. It indicates that the free response means whenever the input is equal to 0, but still you are going to get the output because of the initial conditions. State transition matrix means e to the power of a is equal to Laplace inverse of Si minus A whole inverse. So, free response we are going to represent with the help of the state transition matrix, and this state transition matrix is going to satisfy the homogeneous state equations also. The next point is non-linear elements are sometimes intentionally introduced in order to impose the system stability. Suppose if you want to improve the system stability, sometimes intentionally we are going to add the non-linear systems in the control systems. So, we can say non-linear elements are sometimes intentionally introduced in order to improve the system stability. So, sometimes I want to improve the system stability. So, in order to improve the system stability, I will intentionally I'm going to add the non-linear elements in the control system. So, non-linear elements are sometimes intentionally introduced into the system in order to improve the system stability. So, finally, I can say the non-linear elements are sometimes intentionally introduced in order to improve the system stability. So, finally, I can say the non-linear elements are sometimes intentionally introduced in order to improve the system stability. The next point is discrete data control systems are susceptible to noise. Discrete data control systems are susceptible to noise means they can withstand, they can suppress the noise, or they can withstand the noise. So, discrete data control systems are susceptible to noise means they can suppress the noise or they can withstand the noise. I have already told you, continuous time systems are highly sensitive to noise when compared to discrete time systems. So discrete data control systems are susceptible to noiseless. They can restrain the noise or they can suppress the noise. Next point is feedback can increase the system gain in one frequency range. Feedback can increase the system gain in one frequency range. So, and what I told you, for a positive feedback, the gain is going to get increased. For negative feedback, the gain is going to get decreased. So we can increase the system gain if one range of frequency also we can increase. So with the help of feedback, we can even increase the system gain in one frequency range. So with the help of feedback, we can even increase the system gain in one frequency range also. So with the help of feedback, we can increase the system gain in one frequency range also. The next point is sensitivity considerations are important because physical properties may change with environment as well as aging. Sensitivity considerations are very important because physical properties may change with the environment as well as aging. Suppose if you take a control system, as time goes on, the system parameters are going to get changes. Even with the help of environment also, in whichever environment you are going to keep the control system, the parameters are also going to get changes. Whenever the parameters are going to get changes, there is an effect in the output. So there is an effect in the output. That is called as sensitivity. So sensitivity means because of parameter changes, what is the effect on the output? That is called as the sensitivity. And I have already told you, sensitivity for the parameter changes in the feedback is always greater than the sensitivity for the parameter changes in the Planck transfer function. I have already told you. So therefore we can say the sensitivity in the closed loop transfer function because of the parameter changes in the H of S is always greater than the parameter changes in the parameter changes. So the sensitivity of the M of S with respect to H of S is always greater than the sensitivity of the M of S with respect to G of S, because I already told you, if there is any small amount of parameter change in the feedback element, then there is a huge amount of variation in the output when compared to a small amount of parameter change in the Planck transfer function, which is G of S. So we can say sensitivity of M of S with respect to H of S is always greater than sensitivity of M of S with respect to G of S. So this point always you have to keep in your mind. So therefore we can say sensitivity considerations are very important because the physical parameters may change with the environment as well as the engineering. So whenever you keep any control system in a environment, very hard environment, so based on this, the parameters of the control systems are going to get changes, and even with the help of time also, the parameters of the control systems are going to get changes. So because of this, there is effect in the output. So this is always sensitivity, and the sensitivity of M of S with respect to H of S is always greater than the sensitivity of M of S with respect to G of S. And even the formula, the amount of the sensitivity of M of S with respect to G of S is equal to G of H of S by 1 plus G of H of S. Whereas the sensitivity of the M of S with respect to G of S is equal to 1 by 1 plus G of H of S. This one I already told you so many number of times. So a small amount of parameter change in the feedback will contribute a huge amount of variation in the output when compared to small amount of parameter variation in the G of S plan. So these things always you have to keep in the mind. So by this lecture, we have successfully completed the control system formulas as well as the important points in a very detailed manner. And if you like the content of our channel, then please to like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever you upload new video, the direct notice comes to your mobile. If any improvements needed in our lectures, then please put in the comment section. We will definitely improve all those information in the coming lectures. Thank you so much for watching this lecture. Please, man, take care and bye bye.